Hello, everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Dr. Jonas Latz. Dr. Jonas Latz has been a lecturer in applied mathematics at the University of Manchester since September of 2023. He studied mathematics and scientific computing at Trier University in Germany and the University of Warwick in the UK. He obtained his doctorate from the Technical University of Munich in Germany in 2019, and previously he was a research associate in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. His first academic position was at Heriot-Watt University at Edinburgh, and as an assistant professor. Dr. Jonas Latz, thank you so much for your time today. With this short introduction, you can start.
Yeah, I mean, I guess you can all hear me well, and please feel free to switch on your video, switch on your webcams. It's always nice to, yeah, it's nice to see people when giving a talk. Yeah, I mean, thank you so much. It's a great pleasure to speak in a seminar and to talk to you a bit about our study of physics from neural networks that I think all of you know very well, and the finite element methods that all of you know very well as well. Like associated with this talk is a paper that has been in the archive for a while. And this is joint work with Tamara Großmann, who I think I've seen also in the audience actually, who did literally all of the work. So I'm just here to talk about it. But it's all credit actually is actually going to Tamara. Also, this was also joined with Julia Komorowska and with Carola Schönlieb, who are all at Cambridge at the moment. Yeah, so as I said, this preprint is on archive. You will see some of the results I showed today look a bit different to the archive version because we're currently finishing our revision. So there will be a new version of the archive like early next week, I think, or maybe late next week. And you will then see the figures that you see now in the talk. You will then actually see it in the archive as well. Okay, I will start with a bit of motivation, a bit of background. So motivation, I mean, why do we need to solve PDEs? And I think probably all of you know that already, but I will still talk a bit about it. Then background, what do we mean when we say finite element methods? What do we mean when we say pins? Yeah, because I mean, the idea of the work is to compare these two methods with each other. In computational experiments. Then I will talk a bit about the computational or the experimental setup, show you some results, and then we have some time for conclusions. Okay, let's start with the motivation. So I mean, as you all know, in recent years, deep neural networks have become very powerful tools, or I mean, they've always been very powerful tools, but have become even more powerful for universal function approximation. Yeah, I mean, especially in imaging and in data science, but also in many other fields. Like, for instance, in the solving of partial differential equations. Yeah, and with solving, I really mean the numerical solving. Yeah, so I want to find a function that like satisfies my PDE, and I choose a neural network to do so. And if I find a neural network that satisfies my PDE, I call it physics from neural network, or short PINs. So I will always use PINs, the abbreviation. I think everyone is familiar with that. Now, on the other hand, I mean, numerical analysts have been solving PDEs for decades using, for instance, the finite element methods, or finite difference, finite volumes, spectral methods. Yeah, I mean, there's a very, very large zoo of methods out there. And when we talk about computational tools like pins or like the finite element methods, one important factor is so like how efficient are they when I apply them? Yeah, so which methods gives me a fast solution, which method gives me a good solution, which method gives me like some reliable solution. It's also a point that I come back to in about a slide or so, and that is the purpose of this talk, or the purpose of this work. Yeah, is to compare these like very new methods for example, neural networks to all of the old methods and see, okay, which method is better at what, and take some conclusions from that. So for classical methods, as I just mentioned, there's a rather deep understanding for many PDEs on how these classical methods work. Okay, so we have error estimators, like a priori error estimators. That is, we can often tell what the error will be of our finite element methods or finite element approximation, actually even before we even start using it. Yeah, there is also error estimation when we know what is or when we've already run our FEM code. Um, um, then we can often say tell even better what the error is in the PDE solution. We have convergence guarantees, we have stability guarantees under certain conditions. Of course, like the more complicated PDEs get, the more difficult it is to get error estimates. But for simple PDEs, there has been a lot of research in the last couple of decades. There's also disadvantages. Yeah, so we always get a discrete object in the end. Yeah, so we always boil down the space in which a PDE lives to finite dimensional space. Yeah, we usually need some kind of grid. Which just means that when we get into higher dimensions, this gets basically impossible. There are some ideas on what to do in higher dimensions, but it's very much limited to certain structured settings. Yeah, so like say like lowering tensor approximations and so on. When we talk about machine learning approaches, we kind of lose exactly these disadvantages usually. Yeah, so we don't need a grid. Yeah, we can often use samples, or we can use sort of very strangely structured grids. Maybe like we could use like points from a QMC. QMC means quasi Monte Carlo, for instance, that scale well in high dimensions. That actually may help to delay this cost of dimensionality if you don't need a grid. The evaluation is very, very fast once the networks are trained. So if I say, okay, I need this model and then I want to evaluate it for like a bazillion points, then with classical methods, I usually need to do some interpolation, which is not terribly slow, but also not terribly fast. But when I have a neural network approximated by PDE, I can often just use like a forward evaluation of a neural network on a GPU, maybe even. That will be extremely fast. The disadvantage, of course, is that the theoretical work is not at this point. It's not as far as for classical methods. Yeah, so there are some works, of course, but it's rather limited at this point in time. Okay, let's talk a bit about PDEs. So when I say PDE, I causally mean something like this. Yeah, so we're looking for a function u. Yeah, I assume you can see my mouse. Probably yes. So we're looking for some function u, and we're given some differential operator a and some source term f. And this can really be a very general differential operator. Yeah, so this u here is a function of space and time. Yeah, so space being omega, time being t. And we have this on a closed interval for time. And as I said, okay, we have some differential operator and some source term f, and we'd like to know what the function u is. This looks very linear here, but a could also be nonlinear, of course. Yeah, that's absolutely allowed. In addition to this, we have some boundary conditions. Yeah, so usually we would assume that omega is an open, bounded, and connected like set, like a domain. So we need some information what happens at a boundary, which is just denoted here by general operator b. Yeah, so very often so will just be directly boundaries. Yeah, then b just disappears, and we just know what the value of u is at the boundary. But this could also be like Robber, or could be Neumann. Could be mixed. Yeah, many things are possible. And in case the PD is time dependent, so it actually depends on t, then we need to know what happens at sort of at like some time, usually at like time t equals equal to 0. If you have something that's where the end time of, I think that would happen for like certain financial applications. That's also fine. Yeah, we just don't denote this differently here. So we just say we have some initial value for u. Okay. Now, throughout this work, we look at sort of three different classes of PDEs. Yeah, so we look at certain Poisson equations. Yeah, these are so-called elliptic PDEs. They don't depend on time. They're second order, and they're also linear. That's like what you could use if you want to describe the stationary state of some heat flow, or maybe the stationary state of a Markov process. Yeah, so these will always be elliptic, like Markov process, meaning like an SDE. Then we look at Elenchan equations. Those are time dependent. Also second order. They are not linear. They're actually semi-linear. I will tell you in a moment what that means. And they're parabolic. Um, and what they are used for classically is actually is to describe the separation of like two liquids. Yeah, say in an alloy. Yeah, you have liquid silver, liquid gold. You mix it, and you want to know how these two elements mix with each other or don't mix. And how they look like, we'll show you a plot in a very short amount of time. But what they look like is actually they almost look binary. Yeah, or they seem to approximate something that's binary. Yeah, because they want to tell you in which area of the space you have one liquid, in which area do you have the other liquid, and how do these liquids interact. That's a very similar. It's a very simple PDE, and that has recently especially become more popular also in data science. Yeah, where you say, okay, you don't separate liquids, but you separate data sets. Yeah, so use it for classification or for clustering maybe. Yeah, has been very useful there as well. But classically, it's just a physical model for phase separation between liquids. And then finally, we look at a semi-linear Schrödinger equation. That's also time-dependent, second order, semi-linear hyperbolic, and complex valued. Yeah, so it's a vector-valued PDE. And yeah, it's hyperbolic, so it has a second time derivative, or second order time derivative. And this one is used in nonlinear optics. Yeah, so when you think of Schrödinger equations, you usually think of quantum physics. But the semi-linear Schrödinger equation, I think, is not used in quantum physics, but yeah, like especially in nonlinear optics and all the other similar applications. Okay, let's talk about a finite element method for a very short moment, and let's just think of some elliptic PDE. And what we want to solve with the finite element method usually is we want to find a weak solution of the PDE. So weak solution is something that looks like this. So if you look at this first integral here, that means we're looking for some function u, such that Laplace of u minus f of x in brackets multiplied by a so-called test function v, integrated over the whole domain is equal to 0. And this is supposed to hold for any test function. Okay, so rather than saying, okay, we just look at the PD in the middle, yeah, so this like residual in the middle here, and so this is equal to 0, we actually say it doesn't have to be 0 everywhere. The only thing it has to do is when we hit it with some other function that is sufficiently regular, and then it should integrate to 0. Yeah, so that is like sort of weaker than actually satisfying the strong form of the PDE. Now, what we can do if we want to solve this PDE is we can apply integration by parts, and then we turn this integral up here into this integral down here. Yeah, so we kind of lose the second order derivative here and just get gradients. Yeah, which is particularly nice if there's some like irregular some parts of the P are not super regular. Yeah, so you could have a diffusion coefficient here in the Laplace operator, and yeah, if it's like a Laplace operator, it kind of needs to be continuously differentiable or something like this. But in a weak formulation, you would have it outside of this inner product, and therefore you could now solve PDEs that are not actually PDEs, or they are PDEs, but they're not actually regular enough for a strong solution. Now, if we want to solve this by the finite element method, what we do is we replace the space in which V and U live, and usually it's like some Sobolev space. We replace these by finite dimensional spaces. Yeah, and we say, okay, we have some bases here, and now we just want to solve this weak formulation just on this basis. Okay, so we replace all the V's and the U's by or the V's by basis functions and the U's by linear combinations of basis functions. And then we get such a system down here, and then we can solve the integrals usually analytically, because these functions are quite simple. and then what we get is just a linear system. Okay, so some matrix here that is and some vector here. Now, usually we choose these functions such that B has a particularly nice, nice and easy structure. Yeah, in finite elements particularly. So usually in finite elements you would choose these phi to be locally supported. Yeah, so this matrix B will be very sparse, having many zero entries. Yeah, that might mean that n is actually quite large in many cases. Yeah, there could be thousands or millions without a problem. But the matrix has almost only zero entries, and therefore solving this linear system is extremely fast, even in very high dimensions. But of course, like in other cases, you could also choose these phi i's to be more particular. Yeah, like you could say, okay, it could be helpful for these phi i's to be eigenfunctions of my Laplace operator, for instance. And then I may need very few, but the matrix structure might be not quite as favorable, but at least it's low dimensional, and then I can still solve it. And there are many ideas out there and have been analyzed for the last, yeah, I don't know, 30 years, 40 years, 50 years. Okay, so this was a stationary problem. Now, if we have a time-dependent problem, there's many ways to solve these as well. So, okay, you could do finite elements just also in time. That's possible. The more usual maybe is, or the approach we are choosing is, we use finite elements in space. Yeah, so we find elements for all the Laplace operators, and we use ODE solvers in time. Yeah, because I mean, once you discretize in space, I mean, what you get is it's like a semi-discrete system. It's a very high dimensional ODE, and then you just use your favorite ODE solver for this ODE. And now the problem is, okay, so usually you could just think, okay, like Euler's method. Usually Euler's method doesn't really work because, or I mean, it works, but you need to choose a very small step size. Because actually this Laplace operator will actually lead to a very stiff ODE. And what you should do instead is using some implicit strategy, like the backward Euler method here, or implicit Euler method, which looks like this. Now semi-discrete actually discretes in time. Yeah, where importantly, yeah, here and here on the right-hand side of the equation, you have dependence on ut plus 1 rather than on ut. What I didn't explain in the first place is that this function f does not contain differential operators in our case, but it might be nonlinear. Okay, so while having ut plus 1 on this side might just be okay because it just means you solve a linear system. This might be like slightly annoying because that gives us a nonlinear equation that we would need to solve, and that's yeah, potentially difficult. Okay, then we can write this again as a weak formulation. That looks a bit complicated now, but actually it's not much more complicated than what we've seen before. As I said, okay, this equation is not linear, so we may need Newton's methods to actually solve this in every step. That's very expensive. So one thing we do throughout this work sometimes is use so-called semi-implicit methods. And they're very popular, yeah. So I usually call them semi-implicit strategies. You can also call them like IMAX schemes, like implicit explicit schemes. They've been around for a very long time. And here the idea is that, okay, I mean, we said this equation is very stiff, so we need to use like an implicit method, but the stiffness often is more caused by the Laplace operator, and the nonlinear term is essentially fine. So what you can do is you can solve it implicitly in the linear part, yeah, and explicitly in the nonlinear part, and then what you get in every step is a linear system again. Yeah, and therefore, yeah, so all of the steps are much cheaper than before. Okay, let's talk about pins really quick. And when I say pins, then I actually mean pins based on this original work from Raisi et al. And here the idea is we approximate a PDE solution by a deep neural network, and we call it vanilla pins because it's the basic pins version. What we do here is actually we're sampling the input variables. Yeah, so we say, okay, the input, okay, Yeah, so the input comes from this space omega times the time interval. We're sampling this usually using some not actually random samples, because I mean they not always have the greatest behavior. So I think it's some Latin hypercube sampling that we're using here. And we then try to use the neural network as a function approximator of the PDE solution. Okay, so that means we write down a loss function, and here we essentially plug in the strong form of the PDE into our neural, sorry, plug the neural network into the strong form of our PDE. Yeah, so this was just the PDE. Now replace the function that is a solution by a neural network, yeah, with parameters theta. Yeah, so these are weights and biases, and evaluate this residual that we get here at the samples that we've drawn from this point omega times the time interval. Okay, so we do this for the PDE, we do it for the differential operator, we do it for the boundary conditions. Yeah, then we just sample points in the boundary, and we do it for the initial condition as well. Then we just sample points in space. Exactly. So now, okay, I already mentioned Latin hypercube sampling. What we actually do, and I'm not sure whether this is already contained in the original paper, what we actually do is we resample the collocation friends from time to time. Yeah, so just to get a better coverage of the space. Then what is nice, and I think that's one of the very strong parts of pins, is that we don't need to worry about computing differentially computing derivatives. Yeah, so we can approximate all of these differential operators, or we don't need to approximate them. Yeah, we can compute them precisely, because that's one thing we're really good at with neural networks. Yeah, is actually computing the derivatives of them. And then we have this loss, and we use first the Adam optimizer for some coarse optimization. Yeah, so Adam is very good at getting us in the right range of minimizers. And then we use quasi-Newton methods, that's LBFGS in this case, to actually get down to the minimizer, because I mean in the last step Adam is a bit slow, and LBFGS, so Newton's like Newton's methods are very good once they're close by. Okay, so far so good. Are there any questions at this point? I mean, this was only basic backgrounds. I mean, maybe I'm not sure whether I can see the chat even. Maybe I
No,
can.
there are no questions in the chat.
Okay.
This is clear. Thank you, Jonas.
Okay, very good. Okay. So let's talk a bit about the experimental setup. So first of all, okay, we want to know which of these methods, or for these PDEs that I described, want to compare these two methods and see which one should we maybe use when we solve one of these problems in practice. So for the Poisson equation, we will always have some analytical solution, so that will be fairly easy. So we just compare our pin approximation and our FEM approximation to the analytical solution of the Poisson equation. For Elencan and similarly Schrödinger, we don't have analytical solutions. I'm not sure whether there are cases where you can actually get some, probably not. So what we do here is we actually use finite element method on a very fine mesh. With the backward Euler methods, and actually at least for the Schrödinger equation we use then also P2 finite elements, yeah, to get a reference solution. Yeah, so here I mean we're in cases where we actually have theoretical guarantees for convergence. Yeah, so I think that's fine. Then the settings which you compare FEM and pins is we solve PDEs on different mesh sizes. We choose a semi-implicit strategy for the Schrödinger equation and fully implicit strategy for Elencan. And we use Phoenix for the implementations. So these will always be P1 elements, yeah, just to compare to P2 here. For pins, as I said, we use Adam and then LVFGS. Learning rates are chosen heuristically. Yeah, so kind of for the pins, I mean, there has been done very careful hyperparameter tuning has been done for these experiments. And yeah, and then we train those on different network architectures. I think for some of them we have like 10 different architectures. For others we have much fewer. Yeah, and then actually compare the accuracy and the time. For the training, we're using the Python library JAX, which is very efficient at automatic differentiation. yeah, I mean, I'm rather sure that very similar results you would see when you use PyTorch or TensorFlow. Yeah, but we use Stacks just for convenience. Okay, then as I said, okay, there's kind of three things we compare. We compare solution time. Yeah, so that is for FEM, that is like time to solve the PDE. That it does includes like assembling the matrix. That includes solving yeah, actually solving the equation. And for pins, that is the time to train the network. Then we look at evaluation time. In FEM, that usually means some interpolation methods that can be rather slow and sometimes. Actually, in our examples, it's actually rather slow, as you will see. And for pins, that's just a port evaluation. Yeah, so after training, you now want to evaluate your PDE at multiple points, and that's evaluation time for a pin. And then we look at accuracy, which is like point evaluation. So all of these PDEs, they have strong solutions, so we can do point evaluations. And we have a very fine mesh that is always different from the FEM mesh. Yeah, so it's so we always need to interpolate to compare to the FEM solution because otherwise this would probably be not fair.
Jonas, I had a
Yes,
question. I'm
yes,
Suku
please.
from Davis. I'll see. So in terms of FEM, so why do you interpolate to a different mesh? Because usually with FEM, when you solve a problem on a given mesh, you interpolate on the same mesh because that's where the solution is obtained.
Yeah. No, so here, so in this case, just okay, so the FEM solution is more accurate when you're on the FEM mesh, usually, I think.
Oh, yes, of course.
So here we just want to show like a certain mesh independence. Yeah, and therefore we say, okay, so I think we take the mesh of the ground truth solution because that's like the reference solution, so that would be quite accurate. But we make sure that this mesh does not align with the meshes of the other FEM solutions. Yeah, so we're
Okay.
just trying to be as realistic as possible, and therefore we always interpolate. Yeah.
So it's not that mesh is not nested, right?
No, exactly. It's not nested with the other FEM meshes. Exactly.
Yeah.
That's exactly
Okay.
the idea. Yeah.
Okay.
I mean, of course, if you were to know that you need the FEM solution on that particular mesh, then of course you could do goal adaptivity and all of these things, but we don't do any of this. Yeah, it's just like we do it as basic as possible. Yeah.
Right. Okay. Thanks.
Yeah. And then what we do is we actually use different hardware. Okay, it's the same computer, the same machine, but for FEM, I mean, it's more usual to solve these on CPUs. There is a lot of FEM code out there on GPUs, but it's not as usual. But of course, for pins, we use GPUs because I think that's the only way to train neural networks fast. Yeah, so there's a certain hardware disparity, but I think it is right for the setup in which we want to compare. Yeah. Okay, so let me show you some results. So here it's just a very simple 1D Poisson equation. Yeah, so it looks a bit complicated here, but it's just to get a simple solution in the end. And what we see here is kind of this is just a visual of the solution, and okay, there's kind of one like overly simple neural network that does really badly, and everything else in the Eiffel norm is actually really good. But okay, Eiffel norm doesn't really get us much. So we did some error plots as well, and there you can actually see that like both pins and FEM can both achieve very small errors for this problem. Yeah, so with pins maybe being stuck at like 10 to the minus 8 or so, okay, like ignoring these like single points here. FEM going down smaller, but like 10 to the minus 8 is very good for a solution of this PDE. Yeah, so there's no need to get much further. Okay, if we now compare the computation time versus accuracy, then okay, we see here, okay, we have the relative error. So for the rest of this talk will always be like this. We have the relative error on the x-axis, the time to solve on the y-axis. Time to solve will always be like averaged over, I think, like 10 runs or so, as will be the accuracies. And on the left-hand side here, you see the time to solve, and here you see the time to evaluate. Yeah, so for here, this means, in this case, solving a linear system. This means here for different pins to train the neural networks. And here it means Okay, here it means the interpolation that we're using. And we also put the FEM solving time in there because you could technically say, okay, in some of these experiments, the interpolation is quite slow because we need to interpolate to like thousands of points. Then sometimes you could say, okay, can I just resolve the FEM and I'm still quite fast? Yeah, maybe sometimes yes, other times no. And here we show the evaluation time of the pins. And here, okay, I mean, this is a very, very simple PDE. Yeah, so yeah.
Jonas, I have a question here. What are the orange points, like pings, like the green, red, and purple lines, right? What are the orange points? Because it's also pings.
Yeah, so the points are like the actual setups, are the actual pins, and the lines are just there to connect or to get. I mean, you want to compare pins with like different layer sizes, and therefore we just connect with the
Oh,
points here. So if we just
okay.
put all the points in there, then it's not really clear how they're connected. Yeah, so it's just the lines are just there to explain which points have which numbers of layers. Yeah.
Okay, got it. Thanks.
Okay, and then we see actually that we are really fast at the pin training here. Yeah, so this is about like it's like 10, 11, 12 seconds maybe. Yeah, so the training is really extremely fast for this 1D problem. Okay, so really the code I think is very optimized at this point. But of course, then it's a 1D elliptic PDE, and even if I have an extremely fast pin, it will be very, very difficult to actually beat the finite element method here. Yeah, because finite element method literally is like solving a sparse linear system. Yeah, so that's really, really difficult to beat. And there you see, okay, even for a very accurate PDE solution, you're more in a range of like 10 to the minus 2, or even going down close to 10 to the minus 3 for a more inaccurate solution. But this is like a problem class where it's really, really hard to do anything because it's just so optimized. Okay, then if we go to 2D, and this is kind of yeah, also still a very simple setup. Here now with mixed boundary conditions, some are Neumann monosterically. Again, we have an analytical solution. There we see something similar. Yeah, I mean the pins are actually fairly fast to train. I would say. Yeah, it's more like 2 minutes or so. Yeah, that's for training neural network. Yeah, I mean other like for a generative model also. Yeah, you train for a week. Yeah, and here we train for like 10 seconds. Yeah, that's extremely fast. But also in this 2D case, it's difficult to actually to actually get the error down to the same error that we get with the FEM method. What is interesting here is from the evaluation perspective, I said earlier that the interpolation we're using is not very good, or it's not very fast at least. It's probably good, but not very fast. So here we really see an advantage of pins because now the evaluation time gets extremely fast. Okay, and that's a very nice result.
One question. When you say 20 nodes ping, you mean the 20 neurons?
No, so I think this is well, we can double check in the end. I have all of the so I think it's like number of nodes on every layer for different numbers of layers, I think in here.
Okay.
We can check the very end of the slide with the exact setup. We can double check there because I don't remember right now.
Okay.
But I think it means number of nodes on different numbers of layers. Yeah. Okay, then for 3D, and now this 3D problem is kind of sort of simple in a sense that it's very, very homogeneous. And this actually is a nice problem, I think, for pins, because this homogeneity, yeah, that's literally everything is happening, like what is happening is the same in every direction, is something that the FEM method really cannot use. But pins can use, and here you still see, okay, there's basically no difference between solutions by ground truth, FEM and pins. And here we see actually that that accuracy-wise we get very much in the same area, and speed-wise, okay, it's more like factor 10. Yeah, that's actually not so bad. Yeah, so this is really a problem where pins are getting really more are getting much more interesting. It actually shows that okay, here if we scale up dimension, then classical methods will just get very, very slow. Yeah, the higher dimension gets. But pins don't really seem to mind. Yeah, so there's hardly any speed up from 2D to, or like slow down, I should say, slow down from 2D to 3D, which probably is due to the problem being very well structured and pins being able to capture this like particular structure. Okay, which I think is a huge advantage of pins over classical methods that can't use that at all. Of course, I'm not sure what would have happened if this had been more unstructured. Yeah, I mean, or if there was a diffusion coefficient in here, and pins would not be able to use that because, I mean, as far as I'm concerned, I would assume that this error result is actually fairly independent of, okay, if this gets really, really awful, yeah, then of course the theory will be very different. But I would assume to see the same result for FEM also for like slightly more difficult problems that don't have this nice structure. Yeah,
So
so
Jonas, I had
yeah,
a question on the same point you're raising actually.
yeah,
So if you go back to the previous slide,
yes,
yeah. So instead of just assign functions in all directions, if you had
yeah,
used a localized Gaussian or something, right,
yeah,
at different points in your domain, it'll get much tougher for pins
yeah,
compared to FEM, right? So that might be a fairer comparison, to make the problem a bit more difficult,
yeah,
right? So that, like you said, in terms of pins, the time might not be different, but the accuracy might change.
yeah,
So that
yeah,
might be more interesting to look at. And
yeah,
also another interesting problem to look at, even for Poisson, is problems where you have the maximum principle, for example, right? If you take a Laplacian of u is 1 on the right-hand side with Dirichlet boundary conditions, which are
yeah,
0, then you know that u must be positive, for example, inside the domain. And
yeah,
often pin will not satisfy that. So that's also probably an interesting problem to look at,
yeah.
which we have done before, but
No, I completely agree. So I think we chose this problem particularly because we wanted to see whether in this very homogeneous case, that whether pins would be able to capture this, which they are. So we were quite excited about this. But I mean, you're right. I mean, obviously, I mean, I could put a diffusion coefficient in there that is like very like oscillating differently in different directions.
sure.
Yeah, I mean, it could be like a matrix value, like a tensor could be in there. I mean, you could make this arbitrarily complicated, and the finite element method essentially wouldn't really care. Yeah, so unless it's like an L infinity function, so it gets really irregular. Yeah, then FEM struggles as well. But for many complicated diffusion coefficients, the results would look exactly the same for FEM. But they may be much more difficult for pins, or when you have positivity constraints, like all of these
Right.
things.
Also,
Yeah,
another interesting
great
problem
point.
might be to look at advection diffusion, for example, where
Yeah.
FEM has a lot of problems, right? And then you can see, okay, can pins do a better job for that, right?
Yeah. Yeah, that's an interesting point. I come back to more problems that would be interesting to look at towards the end. Yeah. No, yeah, thank you. Okay. So let's look at some nonlinear problems. I actually thought that this was a great problem for pins, because I mean, as I said previously, what Alan Kant does essentially is kind of a classification. Yeah, so you actually have a function that looks almost binary. It's not binary because it's actually continuously differentiable. Yeah, it actually has quite some regularity. But as you can see down here, what you really get is values that are either close to 0 or close to 1. Yeah, and it is continuous, or it is smooth in between those very, very small interfaces. Here you can actually see them. And that's something that classical methods often struggle with. Yeah, so you often need like adaptive meshes to capture these correctly. Like moving meshes in time. And okay, this is just 1D. Yeah, so time in y direction, space in x direction. And we thought this was a great problem for pins, actually, because I mean, what neural networks are really good at is classifying things. Yeah, so we thought that this would go quite well, but then we tried to solve this problem, and we weren't able to actually find an architecture that would work, which might just be due to the strong formulation, which might be due to very steep gradients. Yeah, that make the problem quite difficult for pins, not so difficult for classical methods because. Yeah, I mean, steep gradients happen, but I mean, it's not often too big a deal. Also, in this 1D setting, of course, very, very simple.
Jonas, can I interject here? Because
yes, please.
I think you need to for boundary layer problems in particular, you have to use the self-adaptive weights the same way. For example, if I finite element method. Even better, I take a spectral element method, which is accurate.
Of course.
And I use very large elements where the boundary elements are, and very fine in the middle of the domain. I will not get the right answer.
Yes.
So the point is the same thing, and Juan has been working with on this. But self-adaptive weights, what we call residual-based attention weights, are very, very important to capture boundary layers.
Yeah.
And so in the original paper, in what you call vanilla pin, of course, that we didn't present there, but since then there was lots of work on dynamic weights, self-adaptive weights, residual-based weights, which is the latest from Juan, and those actually resolve this type of boundary layers. We know because we're experimenting with Reynolds number 2000 in the cavity and 5000 and 10,000. So you can resolve it if you use weights in the loss function the same way, self-adaptive weights, the same way you use a grid so that you can resolve the boundary layer.
Okay.
So it would be 1 over square root of epsilon, for example. You need to have that. Otherwise, if you don't have an element of that size, you're not going to get anything.
That's very interesting. Yeah, I should have look at this.
So weights are very important when you get to boundary layers.
Yeah.
Just like Phoenix would put, the elements very small to adapt to the boundary layer.
But here we don't adapt at all. No, thank you so much. I will have a look. It's very interesting.
Not adapt, but I'm sure you have a boundary layer an element inside your boundary layer. Otherwise, you cannot resolve it.
No.
You will not be able to resolve it. It's not.
No, we certainly have. Sure. I mean, you need to choose the size of the grid small enough to be able to capture this. And here it was very fine, of course. But then we just chose a bigger epsilon. So here these boundary or interface size much bigger. So therefore, what you get in the end is a much smoother PDE. Or the same, the smoothness is probably the same, but you get this effect of this binary effect is actually much smaller. Now we are often interested here in epsilon being very small because Elincan is often used to actually approximate something much more complicated. Namely actually binary PDEs. They do exist, but Elincan often is used essentially as a computational tool to get these curvature flow PDEs correctly resolved. So we chose epsilon to be quite a bit bigger here than here, and this is the grounded solution we want to converge to. Now, when we look at solutions, then we see that for pins, if the architecture is very fine or is big enough, then it's no problem to get a good pin solution in the eyeball norm here. Here for the mesh, given that epsilon is rather large here, this is a very smooth PDE, and so still with a very coarse mesh, you get fairly good solutions. And due to this semi-implicit strategy, they're also extremely fast, actually. So you just need here still 100 of a second. The PDE solution here is essentially, okay, there's time stepping in there, but essentially solving lots of the elliptic equation that we saw in the beginning. And that's extremely fast. And then pins get the error down. So that's certainly fine. But they need much more time for that. Okay. For semi-linear Schrödinger, this actually is an example we took exactly from the Reisi et al. Paper to compare with that as well. So here in the eyeball norm, they all look good actually. When we look at the results, then we look at the amplitude. Usually, that's the most interesting bit. Then we actually see here that the error is again smallest for FEM. Surely makes sense. What is interesting here, and we cannot fully explain this yet. Actually, when you just look at the imaginary part, then the FEM solution is actually worse than the pin solution. So the accuracy is much worse, but also the accuracy everywhere is kind of terrible. So here for the amplitude, it's actually fine for pins and for FEM. So it's O of 10 to the minus 2. So that's fine for all of them. But at the imaginary part is kind of very badly resolved for some reason. I'm not sure where this comes from. And then we also did Schrödinger in 2D. And these are plots you haven't seen yet because they're not yet in the article. So here, what we have is really the 2D version of the last experiment, yeah, with not starting with kind of one blob in the middle, but starting with 2 blobs. That are these like secants terms or secant hyperbolic secants terms, and this is just at time 0. And there, if the architecture is fine enough, it can capture this quite well. What happens at time 0? If it's not, then yeah, okay, it gets difficult. And now, if yeah, we let it yeah, we let the time progress, then it's still fine if the architecture is sufficiently deep. Yeah, so here more layers don't necessarily, sorry, wider layers don't necessarily help. Needs to be deep to get these results down here. And if we let it progress much further, then yeah, it gets very difficult to capture, but also it's a very, very hard PDE to capture. Yeah, the finite element method struggles here as well. Yeah, so here we have symmetry problems, and okay, and this doesn't look, so this up here is the ground truth that we got with higher order finite elements. And I mean, with mesh size 120, 80 looks about okay, but otherwise, this is a very hard problem to solve. Yeah, and here what we see is again, if we compare the errors, I mean, we get like down to 10 to the minus 1 here. We're not very far apart. Yeah, I mean, depending on what like what the goal is, and I think really the difficult bit is really getting the end right, because that's where you get where the waves, where you get this very like wavy behavior. That's very hard to capture. But I mean, for smaller time steps, I mean, it's absolutely fine. Yeah, so there's nothing to worry about. And that's also what you see here. Yeah, I mean, in terms of error, there's not that much of a difference. Of course, there is some difference in terms of solution time. In that case, finite element method here needs like O of 10 seconds maybe, or less than that. And pins are like more like O of an hour or so, or like 20 minutes. Yeah.
So Jonas, I just noticed in that previous slide that 100 nodes was worse than 20 nodes.
So it's which
the slide before, I think so.
The slide before. So these are different. Like it's a different depth. Yeah. So here you have 4 layers with 100 nodes, and you have 5 layers with 20 nodes. Yeah. So that's what I meant by saying kind of the depth seems to have more in that case than getting wider, which. I mean, I believe there's no conclusive theory on like how deep or wide you need to go. I mean, one of the two is the right direction, and here depth seems to be the more important direction rather than width.
But yeah, if you could keep the number of nodes fixed and then increase the depth, you could get a worse solution, right?
That might work here. And I mean, technically, I mean, in terms of universal approximation theory, I mean, either of the two should work. But I mean, I don't think there's a good error estimator for that yet. So it's kind of hard to tell. Yeah.
Also, another question, did you also look at U prime, for example? Because often, you know, in problems, you're interested in the flux or stress or, you know, things like that, the derivatives, right?
Yeah.
So does that accuracy be like 1 order less than U typically? Do you find that, or?
We haven't looked at that. So I mean, I think technically, okay, I'm not an expert on Schrödinger equations, but I think probably if you wanted to compute this with FEM, you would probably use like a mixed formulation, I guess. Is that true? Maybe not. Yeah.
Yeah.
Or you would use like,
I mean, it's challenging for FEM, of course, because it won't be the natural thing to use FEM.
Yeah. No, I mean, for this PDE, I think nobody would use FEM ever. I think. I mean, it's
right,
really a
exactly.
spectral thing. Yeah. So, anyways, this is kind of wild, anyways, to do that. Yeah. No, we haven't looked at this at all. No, it would be interesting to see. Yeah, you would probably use different elements, and you would use like Rabiat-Thomas also, I guess, rather than just like Lagrange P1 elements.
So there's also, yesterday I read a nice article in FEM Review actually on convection diffusion and the challenges with FEM, and recent work. Only people are looking into algebraic stabilized methods, and you know, so there's a lot of open questions with FEM itself.
Yeah,
and
no,
convection diffusion.
yeah, absolutely. I mean, I think FEM research is, it's still very exciting. Yeah, of course. No, it is. No, it is very exciting. Yes. Okay. Yeah, some conclusions, some take-home messages. So I mean, I'm really excited about pins because it's a really cool framework, because it's not like, okay, it's really doing something different. Yeah, it's not okay taking linear approximation of a PDE solution. Yeah, we've done this for decades now, and pins do something very different. That's very exciting. And the problem is I think at this point is that the training is just very expensive, and not that there's any problem per se with pins. It's just that classical methods are extremely fast. Yeah, I mean we've had like, I don't know, like 50 years of numerical linear algebra research on getting sparse linear systems fast, and of course that is very hard to beat at this point. Evaluation cost is quite low after training, but then in certain cases that's like very interesting. In other cases, not so interesting. Yeah, because sometimes, I mean, just resolving the PDE might be quite fast. Yeah, if you say, okay, you need to evaluate it at these points though, and you can just solve the PDE again. Yeah, that's also quite quick. And here, I mean, the interpolants method we used that is built into Phoenix. I mean, that's a bit slow, but of course, with like smarter lookup tables, also you can get this time down quite a bit as well. The parametric case, and I believe George mentioned this already. The parametric case is quite interesting. Yeah, so of course, in like say, I mean, I'm an uncertainty quantification person. Yeah, so usually I need to solve PDEs like thousands or millions of times rather than one time, because I want to do parameter inference, or I have an unknown parameter that I want to sample. And then solving many PDEs, of course, with FEM is extremely costly. Yeah, whilst for pins, I mean, there's a good chance that I train one pin and then use it until the rest of my life, which of course is the optimal case. But then on the other hand, for classical methods, we also have solvers for parametric problems. Yeah, I mean, we have done reduced basis, sparse grids, Gaussian processes, collocation, low-rank tensor. Yeah, so there's a whole zoo out there of classical parametric methods that we then need to compare to as well. Yeah, and then need to see, okay, obviously our pin is now really fast, but is it actually as fast as a classical method that is suited to this particular problem as well? They seem to be really good at high dimensions, and okay, we've seen this for this like very homogeneous Poisson problem, or very yeah, homogeneous, I think is the right word, Poisson problem. And that's actually quite exciting, because I mean, as I said, like beyond 3D, yeah, but classical methods get really difficult to use, and I'll show you an example for beyond 3D in just a moment. And in that case, actually pins seem very suitable, and it's a very exciting direction. Strong formulations seem to be a problem. I mean, there are variational formulations of pins. I think we haven't tried those. And I think in our particular cases, I think they may not be necessary, but that of course generalizes to weak formulations of PDEs then quite nicely. Something as I said already, so something I want to mention regarding high-dimensional PDEs, and I'm not sure whether there's someone in the call that has worked on these before, but for instance, Hamilton-Jacobi-Bellman equations, yeah, they naturally appear in 600 dimensions. Yeah, they're awful to solve with classical methods, but yeah, my friends here have looked at neural network solutions to these. And then actually Tamara has looked at certain non-smooth PDEs. Yeah, so I mean, we are kind of all like from big imaging group. Yeah, in imaging, you often want to solve PDEs that have non-smoothnesses or even singularities in diffusion coefficients, like a one heat equation. Yeah, that we would call like Rudner-Chapademy problem, where classical methods are really bad at. Yeah, it's really expensive, even to solve on a grid. Yeah, and so especially for those, it's very exciting to look at new problems, and maybe we'll look at Tamara's paper in this regard in the archive. And I think that's actually all I wanted to say. I'll just show you a photo from Manchester, and I guess we have time for some questions.
Yeah. Thank you so much, Jonas. That was a really nice talk. Do you have any questions from the audience?
I have a question, Jonas. because the finding about the high dimensions, we had recently somebody from JPL who presented a similar comparison for finite differences. So they found for astrophysics equations, which are basically the Euler equations, compressible equations, they show that in 2D, the finite difference would beat pins in forward problems like you're doing. But then in 3D, pins were faster. Just since we are the topic of high dimensional PDEs, we have used pins in 3 papers we published now in the last 6 months to solve Fokker-Planck that Suku mentioned, the Hamilton-Jacobi-Bellman, which is very difficult for control problems, in 100,000 dimensions in about 40 minutes on a single GPU. And I don't think any method can do that. So it depends on the context. I mean, the other thing I would suggest is that in the title, maybe you want to say that for forward problems, because if you set up inverse problems, I can tell you that pins will be extremely fast compared to, because we have done that. We have done that. Try to find, for example, a hole, a void in a material using boundary displacements. It's a paper that we did. For the forward problem with Abacus, it would take probably 10 minutes for Abacus and 1 hour for pins. But for the inverse problem, it takes 1 hour for pins, but it takes 6 months for Abacus because you don't know the topology. So inverse problems is a totally different game. Or here's a setup that cannot be handled with the classical methods. Let's say somebody hands you one measurement inside the domain. So you have one constraint to satisfy, a very simple constraint. Try to solve that problem with finite elements.
Yeah.
You need to iterate many times. So that's why. But I mean, I've seen these comparisons a lot of times, and in fact, in many. But the other thing that I think your study is not aware of, maybe you were aware of all the self-adaptive weights, the feature selection, for example, for the Schrödinger equation. You need to use the feature expansion. That would work well, because fundamentally there's this issue of spectral bias in neural networks. It doesn't matter if it's called pins or anything else. The spectral bias, you cannot beat it unless you help it with biasing the basis, because you're effectively producing a basis in a neural network, a data-driven basis. So that's what. So there's. So in other words, it's like now, if I compare pins, the vanilla pin that we did, which is we actually developed this in 2016, which about almost 10 years ago. If I compare that with the Courant triangle, which was the first manifestation of finite elements, that goes back now to the 50s, actually, not even 60s.
Yeah.
So I'm not sure why you didn't use all the features that we use in every day. I mean, if you take modulus, for example, of NVIDIA, the implementation of pins, they use adaptive activation functions. They use self-adaptive weights in the loss function. They use feature expansion. They use that as a standard. It's a standard commercial code. Actually, it's given free to the universities. But you chose to compare with the vanilla pin, which is like the idea of Courant on triangles and finite elements, or gyres, to use a Greek guy in the history. But anyway, I'm trying to say that the study I take, so your point is well taken, and sort of we know that since the beginning. But I think I see a little bit of and I know you try to give it a positive spin in favor of pins, but at the end it's not a fair comparison, I think, because you are comparing a Phoenix versus the vanilla pin as opposed to one's version of pins, which could be still, I think it will still be slower. But for example, the Schrödinger example, I'm sure you could capture it, the other layer that I mentioned will become. So in other words, you're trying to balance it, but I think there are some unbalanced components in your study, let's say.
No, I completely agree that this comparison can never be fully fair. Yeah, because I mean, as we just said, I mean, there's been 50 years or 50 more, or like 50 years plus of research, and 10 years of pin research, 50 years of research in these, or probably maybe even longer. But then, to be fair, what we do for the classical methods also is very, very basic. Yeah, I mean, it's literally just using the most basic thing that Phoenix can do. Yeah, and it's not state of the art to what we could do. Yeah, I mean, obviously, if we were using spectral elements probably for Schrödinger, or spectral methods for Schrödinger, this would probably be much faster.
No, but you're not using, sorry, Jonas, but you're not using the linear elements. I mean, no, you're using linear elements, but you're not using the solvers, for example, that Courant or a gyre is using the features.
Yeah, okay. The solver, okay. I mean, we use like a preconditioned CG.
Yeah, you use a preconditioner method, yes, but preconditioners did not exist in the.
Okay. No, that's no, I didn't want to. No, that was
here's
the point
another point. Here's another point. If you want to get good accuracy, even be machine accuracy, there's a paper by Qin-Yao Lai from Stanford, a recent paper, where she uses successive like stacking pins, and she gets the machine accuracy for any for pins for any function regression. Basically, she's tackling the spectral bias problem that I mentioned yeah. Also, if you want to use in three-dimensional problems, if you want to use a separable pin, I didn't do that. The Korean group did it. Separable pins are 60 to 100 times faster than pins in 3D problems. So there is a factor of 100, which will offset the factor that you already have. So look it up. Separable pins is a tensor pin, basically.
No, but then I could also use separable methods. Like I could also use for the 3D problem, I could separate classical methods. I could separate those in 3 PDEs.
Sure.
Would have the same
you can do that. Yeah, you can do that.
So I mean, it's just, I mean, you kind of need to find a setting which you compare in, and the setting will never be fair. Yeah, I mean, there's no, I think there is no fair comparison because the methods are too different. Yeah, they use different hardware. Yeah, first of all, yeah, they're very different in terms of like how much research has been going into them. Completely agree with that. Yeah, I mean, there's no, I just want to argue that what we do classically also is very suboptimal. I think in many senses. And it's not using anything fancy that could have been used just to reflect that as well. But I completely agree. I mean, there's more work there, and I mean, there's so much pin work going on, especially from your group and from many other groups as well. I have colleagues here in Manchester that work on pins quite a lot for very complicated PDEs. And I'm really eager to see what is coming next.
Yeah, may I intervene, George? This is Kostas Hetos from the Department of Mathematics from Naples. So George has put it on the right direction. I mean, there is a lot to be done to bridge or develop new numerical analysis techniques to the pins, right? George mentioned some techniques of this. So, I mean, for at least low-dimensional PDs, there is no way that, I mean, you can beat numerical analysis, also vanilla FEM implementation. However, actually, there is a way to circumvent this. We have worked quite a bit on the forward problem of PDs using random projection pins. George knows about that, where actually you fix the weights between the input and hidden layer randomly. And then what remains is the weights of the output layer. So this is actually a nonlinear, a least squares problem. And there have been a bunch of universal approximation theories from Baron, Ingeling, Pal, etc., where they provide that these are universal approximators. So actually, we have used these. There are some papers on 2021 and also 2023 that we actually have shown with these random projection pins, you can beat FEMs, both in accuracy. I mean, we have solved the Bratu problem in 2D, also the Burgess equation, the viscous Burgess equation with very steep gradients. And we could take accuracy of 10 minus 12 where the FEM could not achieve, but also importantly, with much faster, because FEMs had the problem of approximating these steep gradients, especially in the Berger's equation. So the pins, could beat also in time. So that was encouraging. Of course, the relative advantage of this is in the higher dimensions. So maybe I will send you the references to see.
No, please do. Yeah, no, we're excited to see that.
Thanks.
Thank you so much.
Great. Do we have any other questions from the audience?
Yes. So, hello, Dr. Latz. So, I'm the first author of the papers that scales to 100 dimensions mentioned by Professor Koronakis.
100,000.
So basically, we show that
100,000.
Yeah, basically we show that we have linear costs with respect to dimension with some randomization techniques. When dealing with pin, also in JAX, we use the Taylor mode that can speed up the automatic differentiation because we're using backward mode by default. But if you use Taylor mode, we can get additional reduction in the cost. So I can send you the reference so that you can have a look at it. I think maybe we designed a very interesting Poisson case as yours. So we designed an inseparable solution with a zero boundary condition so that we can vary the dimensionality while keeping the solution to be somehow comparable in different dimensions. And we show the stability of pin and linear cost in both memory and dimensions. Yeah, so yeah, that's what we have done. And I think, yeah, pin, as you mentioned, pins are better in higher dimensions. Yes.
No, thank you so much. Would be very interested in having a look. Yeah.
Yeah, sure. I will send you an email and maybe for further discussion after this seminar. Yeah, thanks for your talk.
Okay. Thank you so much, Jonas. Do you have any other questions from the audience?
I have just a very general quick question. Still on FEM side, I mean, yeah, we can create lots of benchmarks and people would more or less agree on that. But as a general question, you think it would be possible to have some sort of benchmark state of art type of thing on the pin side? Because there are lots of groups, lots of methods, lots of different variations. Would that be even possible to have some sort of image net of pins type of thing?
Yeah, I mean, I think that okay. I mean, I think the problem with some benchmarks is that people then more care about benchmarks than what actual problems. That's sometimes that. I mean, we've seen that a bit. But I think that would be amazing. Yeah, to just say, okay, in future we have these 50 PDEs, or doesn't even need to be 50, but have these 50 problems that behave differently enough, yeah, in order to be interesting. And say, okay, we always test against these 50, and then we know. Also, we could also use for classical methods, of course, as well. And then we see, okay, pins have now beaten like P1 elements. Next, hopefully, I mean, maybe next they can be structure elements, yeah, for different PDEs, of course, yeah, and also the high dimensions where you cannot use classical methods at all, yeah. I think it would be very good to have such a benchmark. I mean, I would be very interested in seeing that.
Erdi, there was a workshop at USC that was focusing exactly on formulating benchmarks. So you can look at that. But one benchmark that has been adopted is mechanical MNIST. You know, like that we have the MNIST, so we can have the mechanical MNIST by Emily. I forgot her last name. She's at Boston University, so that's pretty standard now, and the people. But I think there is consensus, like you said earlier, that trying to come up with an acceptable set of benchmarks, and I think it will happen. It will happen. It will be per field, but I think it will happen. So the USC workshop has some guidelines and some initial problems, but I think it's needed. I mean, Jonas study is useful, but for me, that I've been doing this for living, I've seen these issues. But when we developed pins, we didn't develop it to solve problems, because I have a spectral element solver, which is much better than a finite element solver, and I have a book on that. But what I developed it is for ill-posed problems, for problems where you have some data, even one measurement, as I said. that's sort of, now a lot of people are saying, well, pins don't work here and there, which is a good point, because we know that the pins and neural networks have difficulty in dynamical systems when there is a plurality of scales, spontaneous explosion of scales. So these are things under development. Nobody's sitting idle. Everybody's working hard around the world to do that. But again, like Suku was saying, finite elements could not solve flow problems, advection problems, until the 80s, when Tom Hughes introduced a stabilization method. Even now, they put too much diffusion in the streamwise direction. So the streamwise stabilization is so it's not really a panacea so if you look at an elliptic problem, which is very well posed for variational formulation and so on, and then sure, it's like you have a home court advantage, to use the Manchester analogy, going to play for Manchester United or Manchester City. Then it depends on the court. So, but the advection problems, I think Suku from UC Davis put it right, because that development, the stabilization method of Tom Hughes, was not introduced until the 80s, and still under development. So for 80 years, there was no method, there's no version of finite elements that could solve advection equations, hyperbolic problems.
Yeah, no, I completely agree. I mean, I only need like my elliptic equation with an inlying corner. Yeah, and suddenly things become much more complicated than I think they would be. Yeah, and I like the direction of. I mean, I'm an inverse problems person. Yeah, I mean, I like finding parameters in complicated PDEs. And if I have a PDE that's, I mean, I know half of the physics, I don't know all of the physics. I can replace part of the physics by data, and can do this with a pin. I mean, it's a very, very exciting research direction. Yeah, there's no question about it at all. Yeah, completely agree. Yeah.
Great. Thank you so much, Jonas. It was a really nice talk.
Thank you so much for the invitation. We're very excited to have been able to speak here. That's very nice. So thank you so much.
Yeah, thank you so much for your time. Actually, we have a second talk, so if you want to stick around, it would be nice to have you.
It's actually quite late now.
Okay.
So I think please excuse me, but maybe you can add me to the mailing list, and maybe there are some other talks soon.
Oh, sure. Okay. In that case, thank you so much for your time.
Okay. Thank
great
you.
day.
Thank you, everyone. Take care.
Yeah. Hi, Nicholas. Thank you so much for waiting.
Hey, yeah, no problem. Thanks for the invite.
Yeah. Oh, okay. Today we have a second speaker. Is Dr. Nicholas Boffi, who is currently a Courant instructor at the Courant Institute of Mathematical Sciences. He completed his PhD in applied mathematics at Harvard University, where he was co-advised by Chris Rycroft and Jane Jakes from Harvard and MIT, respectively. During his PhD, he spent a year as a student researcher at Google Brain, where he was advised by Vikas Singwani. He has been the recipient of the NSF Mathematical Science Postdoctoral Research Fellow, a DOE Computational Science Graduate Fellowship, and a Fulbright research grant. In fall 2024, he will join Carnegie Mellon University as an assistant professor. Oh, exciting news. Congratulations,
Thanks.
Nicholas. Okay, with this short introduction, you can start whenever you're ready.
Okay, so it says that the host has disabled screen sharing. Maybe you can enable it for me?
Oh, yes. I'm sorry about that. Can you try now, please?
Yeah. Okay, let's try this. And how about that? Can you see?
Yes, we can see the screen.
And you can see my cursor too?
Yes.
Okay, great. Awesome. Okay, well, thanks a lot for the invite. I really appreciate the opportunity to speak here. So today I'm going to tell you guys about kind of two parallel threads. The first is concerned with the solution of high-dimensional PDEs. So this kind of fits very nicely in with the discussion that everyone was just having after the first talk. And in particular here, I'd focused on solution of the many-body Fokker-Planck equation. And the second thread will have to do with generative modeling, which is a problem in machine learning concerned with sampling from a high-dimensional probability distribution. And here I've worked extensively on a method known as stochastic interpolants. On the left here, I'm showing you a depiction, a spatial decomposition of the entropy production rate for an active matter system, computed using my method for the many-body Fokker-Planck equation. And on the right here, I'm showing you some example generated images using the stochastic interpolant approach. And what I'll show you over the course of this talk is that while these two application domains appear to be rather disjoint, they're actually kind of unified by the same underlying mathematics, namely the Fokker-Planck equation. And we can use advances in generative modeling to develop algorithms to solve Fokker-Planck. And we can use advances in our understanding of the Fokker-Planck equation to develop new algorithms for generative modeling. So there's kind of a feedback loop here where one area informs research in the other area. Okay, and if there's one thing that you take out of this talk, I think probably many people in the audience are already convinced of this, it's that there's many interesting high-dimensional mathematical problems that we simply cannot solve using the standard techniques of numerical analysis, but which we may be able to solve using machine learning. Okay, so let's jump right in. Let's start with a discussion of high-dimensional PDEs. So to kind of understand the setting of high-dimensional PDEs, it's sort of natural to contrast with maybe the canonical low-dimensional setting. And one kind of, example problem that many people think about for low-dimensional PDEs is the Navier-Stokes equations of fluid dynamics. So the Navier-Stokes equations are posed over a physical 2- or 3-dimensional space. It's a coupled system of equations for the fluid velocity field and the fluid pressure field, perhaps subject to some incompressibility constraint. So solving these equations requires estimating 2 d-dimensional fields, namely the velocity field and the pressure field. And because d is low, like 2 or 3, we have many very nice techniques for solving these equations. For example, the kind of finite element techniques that we were just discussing a moment ago. And these techniques work incredibly well for equations like this. They're very, very fast. There's been a lot of research into them over the past almost 100 years now. But they really kind of don't work beyond dimension 3. And this is because they're sort of based fundamentally on spatial discretization. And as soon as you discretize the space, the computational complexity scales exponentially with the dimension. And going from, say, d is equal to 2 to d is equal to 3 is already a significant increase in computational expense. Going from d is equal to 3 to d is equal to 4 is, again, a significant increase, often kind of intractable. And beyond that, it's sort of generically intractable. You really can't do it. But there are many equations that are naturally posed over much higher dimensional spaces that are interesting both academically and practically. So I'll focus on one in this talk, which is the Fokker-Planck equation of statistical physics. And in particular, I'll focus on a specific kind of system, which is an interacting particle system. So I want to study the dynamics of, say, n interacting particles, each of which has d bar internal coordinates. D bar can be different from the physical dimension d, as we'll see in a moment. And this system evolves according to some stochastic differential equation with some drift term bt and some noise term with the diffusion tensor dt. Okay, so I'm showing you an example depiction of one such system below. This consists of 5 interacting particles that kind of follow a moving trap and pairwise repel. And there's a time course of these particles kind of fading out backwards in opacity. Okay, so you can see like a trajectory in time of these guys. So here there's 5 particles and they're in 2 dimensions, and you just need to track the spatial coordinate of each one. So this gives rise to a 10-dimensional SDE. If I now ask, what is the probability that the system is in a given state at a given time, that probability density function evolves according to a Fokker-Planck equation, which I've written down here. Okay, so this Fokker-Planck equation is very easy to write down. You can do it for a generically high-dimensional system, but it's sort of intractable to solve using standard techniques of numerical analysis. This is because solving this equation requires estimation of an n d bar dimensional density. And n times d bar can easily be very, very high for standard techniques, even for rather simple systems. Again, this simple system that I'm showing you below has a 10-dimensional density. And for 10-dimensional densities, the standard discretization-based techniques simply won't work. They're simply far too expensive. Okay, so what are the challenges associated with solving a high-dimensional PDE like this? Well, the first and kind of natural challenge is the curse of dimensionality, which I've already introduced. How can we possibly hope to estimate rho t in high dimension? And the solution here will come in the form of the use of neural networks and machine learning, which at this point, it's kind of well known, they have a remarkable ability to kind of find hidden low-dimensional structure in high-dimensional data, and this can be leveraged to solve high-dimensional problems. Okay, a second challenge, which is sort of unique to the Fokker-Planck equation, is that we're actually estimating a probability density function, and this probability density needs to be normalized. And in fact, even this integral here in very high dimensional spaces, we simply can't compute. So we need to use some kind of architecture that enforces normalization automatically. And the solution to this problem will come in the form of a so-called flow-based network architecture, which kind of gives a nice formula to ensure that we can always compute rho t and always ensures that rho t is normalized. Okay, a third challenge that is unique to the systems of interacting particles that I'm interested in studying is that these particles are indistinguishable. That means they have permutation symmetry. And this permutation symmetry is a very high dimensional symmetry group. In particular, if I have n particles, I have n factorial elements of this symmetry group. And that means that in general, if I have a single mode in the probability density, I'll actually have as many as n factorial modes. Okay, so if I don't account for this in my neural network representation, the only way I can hope to solve this equation accurately would be to have data from all of these modes. And that is kind of generically going to be intractable. So we need to build some kind of network architecture that has permutation symmetry. And the solution here will come in the form of transformers from language modeling, which actually naturally have a permutation equivariance that we can leverage for interacting particle systems like this. And the last question, which is kind of a philosophical question, is let's say I was able to solve this equation. What do I actually want to do with it? Let's say some oracle came down and gave me the solution rho t. Well, this is now a probability density function defined over a very high dimensional space. So I can't plot it. I can't visualize it like I can with standard quantities from applied mathematics and numerical analysis. And moreover, we need to remember that because we have the underlying stochastic differential equation for a given system that we're interested in here, we can already sample rho t just by solving that SDE. And that means we can already compute expectation values of the form that I've given here via the Monte Carlo method. So whatever I get out of solving this equation better be more than the ability to just compute expectation values. Okay, so let's focus on this fourth challenge here. One answer to this challenge, although I believe there are many, will come from the area of active matter physics. Okay, so what is active matter physics? Active matter is a sub-branch of physics that studies assemblies of interacting particles. These are often living particles, and they have some source of internal energy that they can consume to drive a self-propelled motion. Okay, these systems are interesting for several reasons. They're not described by standard equilibrium statistical physics, and that means we need new mathematical and physical tools to understand their dynamics. But moreover, and perhaps more importantly, they often exhibit emergent collective behavior that has no equilibrium counterpart. Okay, and this can range from being practically useful to being kind of academically interesting. I'll give 3 examples. I'm showing them on the left here. The first one is a depiction of a starling murmuration. These are birds that kind of migrate over long distances, and they exhibit these kind of remarkable patterns in their density. And we'd like to understand how and why these patterns form. In the middle here, I'm showing you a biofilm formed of E. coli. Okay, so actually I should have said that here in the starling murmuration, the active particles are the individual birds. Okay, so in the middle here, I'm showing you a biofilm formed out of E. coli bacteria. Here, the active particles are the individual E. coli. What happens here is you have the emergence of a highly non-uniform density from an initially uniform one. It's a fundamentally non-equilibrium phase transition in the sense that this only occurs because the individual bacteria can kind of self-propel in a direction sort of at their own will. Okay, and biofilm formation actually underlies the majority of bacterial contamination, both in water supplies and in medical devices. So we'd really like to understand and perhaps control the formation of biofilms. This is something that we'll kind of focus on a lot in this talk, at least a system that kind of models this type of behavior. And at the bottom here, I'm showing you another system kind of just for fun. This is a drone image from overhead of a herd of sheep kind of migrating across a plain. And what you see is that they exhibit this kind of remarkable polar order in their dynamics, and then they kind of exhibit these sort of topological defects. And if you actually watch a movie of these guys, you see that they actually kind of flow like a fluid. Okay, so a fundamental question that has emerged in this area is to understand when and where these active systems are truly out of equilibrium. So for example, you could ask in the case of this biofilm, now that this system has kind of settled down into this kind of non-uniform density, you could ask, is this an equilibrium system in disguise? More in the sense that could I actually use the tools of standard equilibrium statistical physics to understand what's going on here? Or do I need some kind of fundamentally new physics to really understand the dynamics? 2 fundamental quantities have emerged to kind of understand this question. The first is the so-called system entropy production rate. This is an information theoretic quantity introduced by Seifert in this 2005 PRL paper. What you do is you look at the Shannon entropy of the solution to the Fokker-Planck equation, and you take its time derivative along the Fokker-Planck dynamics. A second quantity, which has kind of been under intense research interest in the last several years, is the so-called total entropy production rate. This one is a little bit more difficult to understand, but we can unpack it. Okay, so there's a symbol KL here. This is the KL divergence. It's kind of a standard distance between probability measures. There's a calligraphic PT. This is the path measure of the SDE over a horizon capital T. There's PT-rev. This is a so-called reverse time path measure. It's kind of an ill-defined object, and there's been a lot of debate in the physics literature about what it actually means. At a qualitative level, what we're saying here is that given a movie of the system's dynamics, we would like to play that movie backwards in time, and we would like to ask what is the probability of observing this backward trajectory under the forward time dynamics. Okay, in other words, this KL divergence quantifies the breakdown of time reversal symmetry or the violation of detailed balance. This KL can scale with time, so you normalize by 1 over t, and then you take the limit as t goes to infinity to avoid any transients. Okay, what I'll show you in this talk is that kind of viewing these systems from the lens of high-dimensional Fokker-Planck equations gives us a canonical way to define this PT-rev, which will also give us a very simple formula for this KL divergence. Okay, so let's introduce kind of a system to focus our efforts on. This is a phenomenon known as motility-induced phase separation. I'm playing a movie of the dynamics here. I think this movie is probably a little bit laggy over Zoom, but you can kind of see generally what's going on. So there's a bunch of interacting particles here. There's 32,000 particles. And what you see is that they've kind of phase separated into a solid-looking object and then a gas that surrounds the solid. Okay, so I'm now going to introduce the dynamics that give rise to this phase separation, and then I'll explain why this is an interesting phenomenon to study. So we'll study a system of so-called active Ornstein-Uhlenbeck particles, although this phenomenon can be exhibited in many other systems. This is a very simple model that exhibits this kind of non-equilibrium phase transition we're seeing at the right here. So every particle has an internal position and an orientation, x and g. The dynamics of position are very simple. Every particle interacts with every other particle in a local way. So if they're on top of each other, they repel. They kind of have just a simple repulsive force. In the absence of these repulsive forces, basically if a particle is in the gas separate from all the other particles, then they would like to swim in the direction gi with velocity v0. This is the active or self-propulsion term. Then there's some thermal noise. Then the orientation evolves according to a simple Ornstein-Uhlenbeck process. So roughly speaking, you can think that this guy points in a fixed direction for time 1 over gamma, and then it changes. Okay, so what happens here is that because these guys are kind of stubborn, you take gamma to be very small, so they tend to swim in a fixed direction for a long time. Two guys sort of ram into one another and kind of get stuck, and another one comes in, another one comes in, and it kind of nucleates a droplet. And at some point, you get the formation of this solid. All the particles on the inside can't get out because of the repulsive forces. The only particles that can get out are on the boundary, but they're constantly being replaced by particles coming in from the gas. Okay, so this is kind of remarkable because in standard equilibrium physics, we only see the existence of condensed phases like this in the presence of attractive interactions. But what I'm telling you here is that we get the formation of a solid with purely repulsive interactions. And this is fundamentally because of the self-propulsion. It's because these guys are kind of stubborn swimmers that keep going in a fixed direction. Okay, so what we would like to do is somehow compute a spatial decomposition of those entropy production rates that I introduced on the previous slide. Okay, and this will be a very fundamentally high-dimensional problem, because if we just count dimension here, I said there's 32,000 particles. Each particle has 4 internal coordinates. That's the d bar from before, 2 position coordinates and 2 orientation coordinates. And so this is roughly speaking a PDE in like 130,000 dimensions. Okay, so how on earth can we hope to solve this PDE in 130,000 dimensions? Well, we'll first kind of take insight from the area of generative modeling, and we'll note the following little simple identity, which is that for any density rho t, I can write its gradient as the gradient of the logarithm times the density itself. In this term, grad log rho, I'll call the score. Okay, this is a very simple identity. It's just because grad log rho is grad rho over rho, and the denominator cancels with this factor of rho on the outside. This is useful because what it lets me do is rewrite the Fokker-Planck equation as a continuity equation. Okay, so what I can do is I can just take the diffusion term and stick it inside the drift with a new definition of a velocity v, where I've just taken b, the old drift, and kind of modified it by this addition of this d times grad log rho term. Okay, so the first thing to observe at this stage is that grad log rho doesn't require normalization. Right? I said at the beginning, one of the problems with estimating rho is that it needs to be normalized, and I can't actually compute that normalization integral in high dimension. The key realization is that grad log rho is actually just a vector field, and I can kind of just estimate it without worrying about this constraint of normalization. Okay, so if I can formulate an algorithm that lets me solve the Fokker-Planck equation by only estimating the score, then I no longer need to worry about normalizing my solution. Okay, so the reason this continuity equation is nice is because I know how to solve continuity equations. I can solve them via the method of characteristics. So that's what I'm introducing here on the right. I'll call the equation that the characteristics satisfy the probability flow equation. So that's written here. R.tr is VT_RTR. This equation has a sort of remarkable property, which is that if I take an initial condition, R, from the initial condition to the Fokker-Planck equation, rho 0, and I solve this equation over a horizon t, then the state of this system will be a sample from rho t at time t. In other words, the flow map of this equation is a transport map from rho 0 onto rho t. Okay, so I'm showing a little graphical depiction of this concept below. So I have some initial condition rho 0. If I look at samples from rho 0 and I evolve them according to this velocity field vt, they end up somewhere else at some later time t. And where they end up precisely corresponds to samples from rho t. Then there's so that's kind of a Lagrangian picture. There's also an Eulerian picture where rho 0 is mapped onto rho t by the flow map RT. Okay, so now I have this kind of deterministic transport map relationship between rho 0 and rho t, and I can ask, what is the change of measure from rho 0 to rho t? And it turns out there's a standard formula that enables me to exactly evaluate the solution to the Fokker-Planck equation. Okay, this formula is given here on the right, and it tells me that rho t, evaluated in a Lagrangian frame that moves with the flow of probability, is equal to rho 0, evaluated on the initial condition, times a change of variables factor, which is the exponential of the line integral of the divergence of v. Okay, so as long as I can compute v, then I can compute this change of variables, and I can solve Fokker-Planck in the sense that I can evaluate the solution wherever I want. Okay, and clearly, if I know b, which I'm going to assume I do, that's like my model for the MIPS dynamics that I showed on the previous slide, then all I need to do is estimate this score term, and then I can compute the solution to the Fokker-Planck equation. Okay, so before I tell you how we can actually estimate this score, let's get some intuition for this new frame of reference, this kind of deterministic probability flow. So if I look at two particles in one dimension, and I just put them on the torus, then it turns out that the system kind of collapses into a closed system of low-dimensional equations. And I can understand the entire dynamics just looking at this kind of two-dimensional effective system given here. All I have to do is look at the difference of the particle coordinates. Okay, and this is very nice because it's a low-dimensional phase space, and that means that I can visualize everything to gain intuition for what's going on. Okay, so if I just roll out trajectories of this system for a long time, it turns out they converge to a stationary density. And I'm visualizing that stationary density here just by binning the samples. Okay, this is just a histogram of the stationary density. Okay, so and this is in the phase space, so this is x and g. There's two modes here. These correspond to basically stable clusterings of the particles. And there's two by permutation symmetry. Okay, I can kind of swap the two particles in the torus. Okay, so this is the stationary density. Now I can ask how this stationary density is built up by individual deterministic or stochastic trajectories. That's what I'm showing on the right. So on the top, I'm showing some example stochastic trajectories from this system. And, you know, they kind of look like standard stochastic trajectories. They're very rough. They kind of bounce around all over the place. They're super noisy. You can see that they spend some time in one of the modes, and it looks like they transition from one mode to another, but it's not totally clear what's going on from these stochastic trajectories. By contrast, on the bottom here, I'm showing a phase portrait of the probability flow equation, which exhibits some remarkably simple closed limit cycles. Okay, so it almost looks like a pendulum. And what you see is that the dynamics of this system in phase space just corresponds to kind of oscillations. And these actually correspond to oscillations of the two particles kind of about a fixed distance from one another. Okay, so that's intuition for the probability flow. Now we can ask why the probability flow kind of gives me the solution to the problem that I posed at the beginning, which was estimation of these entropy production rates. So I have an expression for rho t. The system entropy production was the time derivative of the Shannon entropy. I can just plug that expression for rho t directly into the definition of the system EPR, turn the crank a little bit, and you can find that, in fact, I have a very simple expression for the system EPR, which is that it's just the expected divergence of V at time t. In other words, if I think about this system like a fluid in high dimension over the high dimensional phase space, then it's just the expected incompressibility of the fluid. Okay, now I will go one step further because I'm looking for a spatial decomposition of the EPR, which is that I will define a so-called stochastic EPR at a point in phase space, which is just the argument of this expectation, just the divergence of V. Okay, I'm visualizing this on the right here for my low dimensional system over the phase space. Remember that the dynamics correspond to closed limit cycles. Okay, so what this says is that there's entropy production when the particles collide, and there's entropy annihilation when the particles leave the collision. Okay, so this is identifying something very fundamental about particle-particle collisions from the perspective of entropy production. Okay, so this is now kind of a point-wise quantity over phase space, but for my MIPS system, where say I have 32,000 particles, that's still a 32,000 dimensional phase, or actually 130,000 dimensional phase space. So this, as written, isn't necessarily very useful. But for particle systems, I can actually go one step further, which is that I can recognize that this divergence splits into a sum over lower dimensional divergences over the individual particles. Okay, so what this lets me do is break down the system EPR into contributions from the individual particles. And then I can say, take a snapshot of the system and color the particles by their contribution to the EPR. And that will give me the spatial decomposition that I'm looking for. Okay, so this is kind of where we're going. Now, that was the system EPR. At the start, I also introduced this total EPR, which had to do with the KL divergence between a forward time path measure and a reverse time path measure. And we said that it wasn't clear at all what this reverse time path measure should be. Okay, so we can kind of give a sort of canonical definition for this reverse time path measure by looking at the system from the perspective of this high dimensional FPE. So what I can do is I can play the same game that I played earlier and use this identity for the score to move the diffusion tensor into the drift, except I can go one step further. And rather than moving the diffusion into the drift, I can flip the sign of the diffusion and then again change the drift to account for the fact that I flipped the sign. Okay, diffusion is stable forwards in time. It's unstable backwards in time. That means that anti-diffusion is stable backwards in time and unstable forwards in time. Okay, so this gives me a canonical reverse time SDE that I can write here, where I just take the drift of this equation and then I take some reverse time Wiener process. Okay. Now, I have a well-defined forward time dynamics, which is just the system dynamics I introduced before. I have a well-defined reverse time dynamics, which is just this equation here. And I'm asking, what is the KL divergence between their path measures? It turns out there are standard tools in stochastic analysis to compute this, namely Girsonov's theorem. And if I just apply Girsonov's theorem, and again, turn the crank a little bit, under the assumption that my system has a stationary density, I again find a very remarkably simple equation for the total EPR, which is that it's just the expected square norm of the velocity v weighted by the inverse of the diffusion tensor. Okay, so one can see that from the perspective of EPR, this velocity field v is very fundamental. Its divergence is the system EPR, its square norm is the total EPR. Okay, now I'll play the same game that I played before. I'll define a stochastic total EPR at a point in phase space as the argument of this expectation. So it's just v squared in the d inverse norm. And then I'll observe that because square Euclidean norms split into square Euclidean norms over the individual blocks, I can again break this down into a sum over individual particle contributions. And that will again enable me to color a snapshot of the system by the relative contribution to the system EPR. Okay, I'm showing you a depiction of this total EPR over the phase space for my low dimensional system on the right. Again, let's recall that the dynamics correspond to closed limit cycles. So what we see is something very similar to what we saw earlier, except we've kind of lost sign information. Okay, so this point here is the particle-particle collision, and we see that entropy production is dominantly concentrated there. Okay, so everything I've said so far has been under the assumption that I have the velocity field v. But of course, this velocity field v depends on the score grad log rho, and I don't actually have the score. Right. In fact, it appears that there might be some kind of conservation of difficulty because somehow I'm assuming knowledge of some component of the solution for all the calculations I've carried out so far. But it turns out in recent years, there's been a lot of work devoted to estimating score functions in the context of generative modeling. And we can take insight from this progress to design an algorithm to estimate the score to solve the Fokker-Planck equation. Okay, so for any density rho, I can define the so-called score matching loss function. You should think of rho as being, say, the stationary density of the Fokker-Planck equation for the MIPS dynamics, but this is true for any density rho. So if I just look at the L2 error between some score model, h hat theta, and the target score, grad log rho, this is kind of a very natural loss function, right? For example, it's strongly convex in a functional sense. It's lower bounded by 0. It's always non-negative. It has many very nice properties. But as written, it's actually not useful because it's unknown, right? I don't actually have observations of grad log rho, so I can't actually compute this thing. It turns out it was observed by Hyvarinen in this 2005 paper on the bottom here that if I just expand this square and then I integrate by parts, I end up with an equivalent implicit loss that is actually tractable. All I need to do is compute the divergence of my model, and I can do that using standard techniques of automatic differentiation. For example, if I represent h hat theta as some kind of neural network. Okay, so now in practice, what I can do is I can take this expectation over the stationary density of my system, and I can approximate it via Monte Carlo, right? I can simulate the SDE to generate a big data set of samples. And then I can approximate this integral just by an empirical expectation. And then I can minimize this guy using standard techniques, for example, stochastic gradient descent and approximating h hat theta by some neural network. Now, let's recognize that all that appears in this loss function is a square norm and a divergence. We already showed that square norms and divergences split into contributions from individual particles. So I can actually break down this loss function into a sum over individual particles. Okay, the first line here says that I should think of a single snapshot of the system as being my data. While the second line actually suggests that maybe I should think of the individual particles as being data. This is a very natural way to think about the system because I have indistinguishable particles. There's permutation symmetry. And it sort of suggests that perhaps I should parameterize the particle score, the score for a given particle, and then I should batch over the particles as if they were the data. Moreover, because this is a physical system, we expect by spatial locality that, say, the entropy production for a given particle should somehow only depend on some local neighborhood. The entropy production for a given particle shouldn't depend on some particle that's super, super far away that this guy never sees. And so I can actually parameterize the score in this way so that the score for the jth particle only depends on nearby particles. Let's get some kind of graphical intuition for what I'm saying here. The first line of this equation says that I should think of this entire snapshot as being a sample to approximate my loss. The second line says, let's think about all of the individual particles as being samples. So when you think about it in this way, there's actually much more data in a given sample from the stationary density. Okay, so in one moment, I will introduce the actual neural network architecture that we use. This loss function here will be kind of the main workhorse for the results that I'll show you. But I just want to comment on a few other loss functions that we can also use. One of these is the so-called pin loss, which we also introduced in this paper. So for systems at stationarity, I can always write the Fokker-Planck equation as the divergence of v times rho equals 0. This just comes from the Fokker-Planck equation I wrote down earlier as a continuity equation. I've just set dt rho equal to 0. Okay, so if I expand this divergence and then divide by rho, it turns out that this can be written as a closed equation just in terms of the score. Okay, and this suggests the use of a pin type loss, where I parameterize the score, again, using some neural network as h hat theta. And then I just define a loss, which is just the expected square residual for this stationary Fokker-Planck equation averaged over the stationary density. And here I've taken some model v hat theta, which is just constructed using my approximate score model. Okay, and we actually use this in many experiments in the paper, and we find that it can significantly improve accuracy relative to just using score matching alone. Okay, I also want to highlight some other work. For the majority of the results that I'll show you will be in the context of stationary problems, namely MIPS, but we've also introduced methods for solving the Fokker-Planck equation for time-dependent problems. Okay, so one can show, for example, that if I consider my model density to be the push forward of my initial condition under my time-dependent flow map, that the time derivative of the reverse KL divergence from my model to the target is upper bounded by something that looks a lot like a score matching loss function, except there's something a little bit different about it, which is that actually the score of rho t, the target density, doesn't appear anywhere in this equation. If you look closely at this equation, what you see is that this is the expected error between my score model, h hat theta, and the score of my model, rho hat t, averaged under rho hat t. So what this suggests is a kind of self-consistent score matching, or a so-called self-consistent Hyverian loss function, where again, I play the same game that I played before. I integrate by parts to eliminate this grad log rho hat t term, which I don't have access to, and I rewrite this just in terms of a divergence. Okay, now average over samples produced from my model. Okay, we call this approach score-based transport modeling because it's quite related to score-based diffusion methods, but it has this kind of difference that we're estimating a score self-consistently along data that we produce. Okay, it leads to a very natural sequential or time-stepping based algorithm that we call sequential score-based transport modeling, where the basic idea is to control this reverse KL divergence by sequentially controlling the time derivatives at each t. That gives you a way to step from time t to say t plus delta t. Okay, and what you can do is you can always write down your approximate probability flow equation, which I've written here, where I've just plugged in my approximate score model. And I will just always define at any time t my score model to be the minimizer of this SBTM loss function. Again, say parameterized over neural networks. And then to convert this kind of continuous relation into an actual practical algorithm, what I can do is I can discretize this probability flow equation with an ODE integrator, pick your favorite off-the-shelf ODE integrator, and I can always approximate this expectation here via a collection of n samples that I'm propagating along the probability flow. So I can start with n samples from the initial condition to the Fokker-Planck equation. I can push them according to the probability flow equation, and I can sequentially alternate between estimating the score on those samples and then pushing those samples forward to again estimate the score. Okay, and those results are kind of contained in this machine learning science and technology paper cited at the top here, but in the next few slides, I'll focus mostly on results for the stationary Fokker-Planck equation. Okay, so now let's describe one final ingredient, which is the actual network architecture that we use. So remember that I said at the beginning, the key symmetry in this problem is that the particles are indistinguishable. That means that the density rho is permutation invariant. So if I change the labeling of the particles, the density doesn't change. Okay, it turns out that permutation invariance in rho actually leads to permutation equivariance in grad log rho. What this means is that if I relabel the particles, I need to kind of permute the components of the gradient in an analogous way. This is very natural. It's essentially just because the gradient has individual slots that correspond to the individual particles. So if I relabel them, I need to relabel these slots. Okay, at first glance, it's actually not so clear how to write down a permutation equivariant neural network that will actually be expressive enough for these kinds of very high dimensional systems that we're interested in. At some point when Eric and I were thinking about this problem, we realized, in fact, that transformers are permutation equivariant. Okay, transformers have been highly influential. They've sort of revolutionized language and vision, introduced by this 2017 Baswani paper, which now has over 100,000 citations. The key insight is that transformers, often used in language, but now in vision as well, kind of build up the output by learning interactions between tokens. In language, tokens are words. In vision, tokens are patches between patches of the image. The basic idea is that since we're studying an interacting particle system, we should think of the particles as being tokens, and we should build up the score by learning potentially high-order interactions between these particles. I think this is a very exciting idea because of the huge impact that transformers have had in language and vision, but I really haven't seen much application of these kinds of ideas in soft matter where I think they can be very naturally applied. Okay, so I don't want to spend too much detail on the specifics of the network architecture itself, although I'm happy to answer any questions. This is just because it's kind of easy to get bogged down in these sorts of diagrams. But the basic idea is as follows. I take all the particle positions and I take all the particle orientations and I embed them into a higher dimensional space using a learnable MLP embedding. And then I just concatenate these guys and I view them as the tokens. Okay, I pass them to a transformer encoder. The key ingredient in a transformer encoder is the so-called self-attention mechanism, which computes these interactions between the tokens essentially by learning weighted dot products. Okay, you do this a bunch of times. The first time you do this, you learn 2-point interactions. The second time, you learn 2-point interactions between the 2-point interactions. So you have 4-point interactions. Every time you do this, you kind of double the order of interactions. We use 4 layers, so we have up to, say, 16-point interactions. Okay, and then you can take another learnable decoder for the output of this transformer encoder, and then you get your score just by processing everything through this. And you can just learn this guy in an end-to-end fashion, just backpropagating through all of the parameters. Okay, so for our, say, 130,000 dimensional system, we found good results using around 1 million or 2 million parameters in this kind of model. Okay, so now I want to show you some results. So what I'm going to show you here is a movie. On the left, it's a movie of the MIPS dynamics with 4,096 particles, roughly speaking, a 16,000 dimensional Fokker-Planck equation. In the middle, I'm going to show you the total entropy production. And on the right, I'm going to show you the system entropy production. Okay, and again, it's probably a little bit laggy over Zoom, but you should be able to see the gist here. Okay, so what you see is that both definitions of the entropy production concentrate on the interface. Again, maybe just to be clear, what I'm doing is I'm using this particle decomposition of the EPRs that I displayed earlier with a learned score. Okay, so when we got this result, we were very excited because there are predictions in the theoretical physics literature, both from a kind of field theoretic perspective and an information theoretic perspective, that qualitatively this should be the structure of the entropy production in these kinds of systems. But no one has ever been able to compute these quantities directly from their microscopic definition before because of the underlying high dimensionality. And I simply don't see a way you can do this without machine learning. Okay, so that's very interesting. Now, one thing we realized after generating these results is that since we parameterize the score at the particle level, and since we parameterize the score in kind of a local way, where the score for a given particle only depends on a local neighborhood of particles, our network model actually doesn't know the total size of the system. And what this means is that we can train a single model at a fixed system size, and then we can use that same model for larger and larger systems to investigate the structure of these kinds of signals in the thermodynamic limit. Okay, so what I'm showing here are some results for the system EPR. Learned for n is 4096, and then just extended to higher dimensional systems without any additional retraining. What we see is something very, very complementary, which is that as I increase the number of particles in the system, the cluster gets more and more stable, and the signal kind of concentrates even more on the interface. Okay, we can play the same game with regions of the phase diagram. So what I'm showing here, I'm varying the packing fraction, and here I have 8,192 particles. I trained with a packing fraction of 0.5 for 4,096 particles. So I'm kind of generalizing in two separate ways here. And again, I'm showing the system EPR. So for very small packing fraction, there's essentially no particle-particle collisions, and then there's essentially no EPR. As I increase the packing fraction, there's no dominant MIPS cluster, but there are kind of little clusters that form all over the place, and you see kind of sporadic entropy production spread throughout the system as a result. I increase the packing fraction further, and I see the cluster that I saw earlier with an interfacial signal. Increase it even more, and now the cluster kind of starts to dominate the system. And again, it's kind of an interfacial signal. And then finally, if I increase it enough, the situation sort of inverts, where it's mostly a solid with a bubble of a gas inside of it. And again, we kind of pick up this interfacial signal just between the gas and the solid. Okay, now I want to show you just two more movies of these results. It's the same kind of movie as we saw before. On the left is the system dynamics, the middle is the total EPR, and the right is the system EPR. So this is 8,192 particles. This is a 32,000 dimensional Fokker-Planck equation. And we see a very similar signal to what we saw before, but the cluster is kind of dynamic, okay? If I now move up to 32,000 particles, roughly 130,000 dimensional Fokker-Planck equation, the cluster becomes super, super stable, and we get a very, very clean interfacial signal. Okay, and I think sort of as George said earlier between the two talks, it's just kind of remarkable to me that we're actually able to say something about a PDE in 130,000 dimensions, and there's really no way to do this using the standard techniques of numerical analysis. For example, if you try to use finite elements on a system like this, you will not be able to compute anything. Okay, so this is what I wanted to show you in the context of active matter. Maybe I can pause for a moment and ask if there's any questions, and if not, then I'll move on to using Fokker-Planck equations in the context of generative model.
Okay, do we have any questions from the audience?
I have a question more on the modeling, because I see all the systems are modeled with the same stochastic ODE. And years ago, we were looking at flocking, and we consider non-local interactions using fractional calculus. So actually, it turns out that there are non-local interactions, which somehow we ignore. And just to give you an idea, if I put a interface somewhere there, you're sort of in the open, right? That you assume no boundaries or no interface. But if I put an interface, normal statistics are thrown away. You don't have normal statistics anymore. So you have this outlier, you have different So I was wondering, from the physics point of view, which is this really a realistic equation, or is it just a good model to write papers?
So I can tell you that it's a model that has been of intense research interest. I think it's kind of one of the simplest models that you can write down that exhibits a non-equilibrium phase transition, really that exhibits MIPS, which is kind of observed widely across active matter experiments. So I think it's very much liked because it's so simple and still exhibits this phase transition. Whether or not it kind of quantitatively reproduces results of interfaces and things like that in the lab, probably not. But I think from the perspective of trying to understand the new kinds of phenomena that can occur in non-equilibrium physics, it is a very good model. If you want to kind of have engineering accuracy, then probably not. You need to do more complicated things, maybe with fractional calculus, like you're saying.
Yeah, I think the model I was using actually for bear flocking was the Smole, what's it called, the Smole something model, Smole, so which we converted to a fractional with Levy noise, and that actually produced better results. And that, of course, you don't need Gaussian statistics. You don't need the Wiener processes to do the Wiener increments to do that. But anyway, yeah. Thanks. Because when you send us the paper, there was so much physics there, but now I kind of followed. Thanks very much for this part. Yeah.
Yeah, so
Please go
actually,
on.
Eric and I are now looking at flocking models as well, in particular the V-Sheck model. So I think it's a little different than what you're describing because it's still Gaussian noise and it's still kind of a standard Fokker-Planck equation. But yeah, we're also kind of pushing to these other kinds of systems that exhibit other kinds of phase transitions as well.
Thank you. Yeah, please go on.
Okay, great. So everything I've said so far has been kind of in the context of high-dimensional scientific computing, using techniques from generative modeling, namely estimation of the score. What I want to do now is kind of flip this around and show you how we can use insight from the analysis of high-dimensional Fokker-Planck equations to develop new techniques for generative modeling. Okay, so what is the generative modeling problem? Well, I'm given samples, xi, I going from 1 to n, from some target distribution that I'll call rho 1. Okay, it'll be clear in a moment why I call this distribution rho 1. So you should think, for example, that rho 1 is the distribution over natural images, and these xi's correspond to individual images. Okay, and what I would like to do is form an estimate, call it rho hat 1, of rho 1. That's close in some sense. Pick your favorite distance metric, KL, Wasserstein, etc. I would like that to be small. And then I would like to generate new samples, x hat I, from rho hat 1 to approximate samples from rho 1. Okay, again, in the context of image generation, I would like to generate new images that look like real images. So implicit here is that whatever estimate I form, it better be easy to sample. Okay. So there's many approaches to solve this problem. One that has kind of gained a lot of traction in recent years, and one that I will take in this talk as well, is to try to build an ODE or an SDE such that if I draw an initial condition from rho 0, where rho 0 is some known simple distribution like a Gaussian, for example, then the state at time 1 will be a sample from rho 1. Okay, then the main question here is how do we actually design the drift field that enters this equation so that it accomplishes this task? Okay, so what we will do is approximate this ODE or SDE as, say, x hat t with some learning algorithm. And then I'll take my model distribution rho hat 1 to be the law of x hat 1. Okay, so that means that I can actually efficiently sample rho hat 1 just by solving an ODE or an SDE. Okay, but implicit in this formulation is that not only do I need to design this field B that does the right job, but I need to design it in a way such that it's variationally tractable. Right? I need to be able to characterize it as the minimizer of some optimization problem. Okay, so let's get some kind of insight for this problem. By the way, I have a timer running. I'm at 40 minutes. I'm going to end in, say, 10 minutes or a little more. It's 2, but I guess we started a bit late. So
Yeah, don't worry. Take your time. There's no hard timer, so please.
Okay, it's like 10
take
more
your
minutes.
Time.
Or so.
No, take your time. Don't worry. Don't worry about that.
So a lot of progress has been made kind of within this formulation in recent years with the advent of so-called score-based diffusion by Yang Song, in particular in this 2021 iClear paper. So the basic idea of score-based diffusion is as follows. You take a sample from your target distribution, like an image, for example, this image of this puppy here, and you pass it through a very simple stochastic process, like an Ornstein-Uhlenbeck process, that converts this image into pure noise. Okay, in other words, it maps the distribution rho 1 into just a standard normal distribution. And then you ask, is there a stochastic process that kind of reverses this noising process? In other words, it takes a sample of pure Gaussian noise and it converts it into an image. It was actually shown by Brian Anderson in 1982 that such a stochastic process does exist. I've written it at the bottom here, and it depends on the score, which, as we know very well by now, we've been estimating quite a lot in the context of active matter physics. In fact, this time reversal here is precisely the time reversal that we used in the context of active matter to define the reverse time path measure. Okay, so it is very hard to understate the impact that this algorithm has had on the field. It's been pretty revolutionary and it works amazingly well. For example, Midjourney, DALL-E, ChatGPT, all these guys for image generation use an algorithm based on this kind of diffusion approach here. But as written, there's a few flaws that perhaps one would like to correct. Okay, so for example, this Ornstein-Uhlenbeck process, while it does converge to a Gaussian, it only converges on infinite time. So in practice, we need to truncate at some finite time, capital T, and that introduces a bias. And it's actually not possible to avoid that bias when using a score-based diffusion model like this. Second, somehow this noising process is sort of fundamentally tied to, somehow the generation process is fundamentally tied to the noising process in the sense that you think about noising an image and then you think about reversing that noising process. And maybe it doesn't have to be this way. Maybe you can kind of generate samples in a much more general manner. And finally, it's very hard to change this forward noising equation so that it converges to something other than a Gaussian, right? You can very easily write down equations that have complex stationary distributions. For example, you can write down some Langevin dynamics. But if you want that equation to converge fast, you're sort of stuck to kind of stable linear systems like is used here. Okay, and that can significantly reduce your flexibility because maybe you want to use a base distribution rho 0 that is not a Gaussian, but is something kind of tailored to the target. Okay, so what I'll show you over the next couple of slides is that by looking at this problem from the perspective of high-dimensional PDEs, we can eliminate all of these restrictions. Okay, so the way we'll do this is we'll introduce something called a stochastic interpolant. So a stochastic interpolant I'll define as the following stochastic process. I take x0, which is a sample from rho 0, x1, which is a sample from rho 1, and z, which is a standard normal, and I take a linear combination of them, a time-dependent linear combination. Okay. The coefficients alpha, beta, and gamma need to satisfy some boundary conditions. Namely, alpha starts at 1 and ends at 0, beta starts at 0 and ends at 1, and gamma starts at 0 and ends at 0. Okay, so kind of as a canonical example, which we often use in practice, actually, you can take alpha to be 1 minus t, beta to be t, and gamma to be square root of t1 minus t. Okay, so this corresponds to a linear interpolation between x0 and x1. And then this gamma comes from the Brownian bridge, if you're familiar with that. Okay, so what are the key properties of this stochastic interpolant? Well, it satisfies the right boundary conditions. Namely, because of the boundary conditions I wrote down on alpha, beta, and gamma, at time t is equal to 0, it's a sample from rho 0. And at time t is equal to 1, it's a sample from rho 1. It's easy to sample. I can just compute xt explicitly using samples x0 and x1, because I can always draw fresh Gaussian samples, for example. And the base distribution here, rho 0, is arbitrary, and it can be tailored to rho 1. Okay, so for example, I can set it to be a Gaussian, like in score-based diffusion, but I can also set it to be sort of whatever I want, as long as I have samples from rho 0 or can generate them. So let's get some intuition for what I'm describing here. So I'm showing you 3 different choices of interpolant. Here, my base distribution is a distribution over white flowers, and my target distribution is the distribution over purple flowers or a Gaussian. Okay, so in the first row, this is actually the example that I gave on the left. I convert this white flower into a purple flower with a bit of noise in the middle. In the second row, I do something rather similar, except I devolve into pure noise in the middle. And on the bottom, I'm showing you just a linear interpolation between a Gaussian and a white flower. And this is something like score-based diffusion, except it happens exactly on finite time. Okay, so there's no bias here. On 0, 1, it converts the white flower into pure Gaussian noise. Okay, so this is what happens at the level of the samples. One can also ask what happens at the level of the distribution. And the key realization is, in fact, that once you define an interpolant xt, you actually define a path between rho 0 and rho 1 in the space of measures. Okay, so here, different rows correspond to different interpolants, and different columns correspond to different times. Okay, so my rho 0, my base distribution, is a 2-mode Gaussian mixture, and my target distribution, rho 1, is a 3-mode Gaussian mixture. And what you see is that the choice of the interpolant changes the structure of the intermediate density. But in every case, rho 0 is kind of smoothly deformed into rho 1. And in fact, I can perhaps control the structure of the intermediate density and try to make it as simple as possible by choice of the interpolant. So a key thing to realize at this stage is that this process here defines some kind of dynamical transport of measure. And what I would like to do now is actually characterize that dynamical transport analytically using the language of high-dimensional PDEs. So we can do so as follows. Here's a theorem. The time-dependent density, rho tx, of the interpolant xt satisfies the following potentially high-dimensional transport equation, where the drift entering this equation is just the conditional expectation of the time derivative of the interpolant, given that I'm at a certain point in space x. Okay? So what this means, if I want to know the drift of this equation at a given point, I look at every possible interpolant that can go through that point, and I average all of their time derivatives. Okay? Now, we can take some insight from the work we did in the first half of this talk on Fokker-Planck and recognize that if I have a transport equation, well, as long as I have the score, then I also have an infinite family of Fokker-Planck equations, right? I can always, for any time-dependent diffusion tensor, as long as it's non-negative, introduce some diffusion term here, and I can cancel that diffusion term by modifying the drift to have an appropriate score term. And in fact, when I do this, I don't change the intermediate density at all. It's the same rho tx that satisfies all of these equations. Okay, so we'll get into how and why you might want to choose epsilon as we proceed in the next couple of slides. When I first introduced these models, I said that something that we need is that the drifts entering the equations need to be variationally tractable. And it turns out that both B and the score are indeed variationally tractable in this context. So because B is simply a conditional expectation, one can actually estimate it using a quadratic loss function. I've given this here. It's very simple. It's just an expectation of, say, some neural network model squared minus twice a dot product between that network model and x dot. Okay, and this just follows essentially by the L2 projection characterization of a conditional expectation. It's very simple to show that the unique minimizer of this loss is precisely this conditional expectation here. There's an equivalent loss for the score. This one is not as easy to see, but it turns out that you can characterize the score as a conditional expectation as well. And then you get a very similar loss function, where instead of trying to fit x dot, the score tries to fit negative the Gaussian noise z divided by gamma. In fact, this is why we introduced gamma times z, precisely so that we would have this loss function for this score. Okay, so let's get some insight for how we could actually sample these equations. So if I want to sample that transport equation, I can play the same game that I played in the first half of the talk, and I can solve that equation via the method of characteristics. Okay, so this gives rise to an underlying probability flow equation, very similar to what we were doing earlier in this talk. I just look at an ODE where the right-hand side is given by the drift B from the continuity equation. And this probability flow equation has a very nice property, which is that if I draw a sample from my base density rho 0, then at time 1, the state will be a sample from my target density rho 1. Similarly, for these Fokker-Planck equations, I can look at the underlying stochastic dynamics. Now it's a very similar equation, except it's modified by epsilon of t times the score, and then I have some noise term here. And again, this SDE satisfies that if I draw an initial condition from rho 0, then the state at time 1 will be a sample from rho 1. Okay, so if we visualize this qualitatively, what I'm doing here is my columns correspond to different choices of the interpolant, and my rows correspond to different choices of epsilon. What you see is that, in fact, as we change the scale of the diffusion, we don't actually change any of the one-time marginals, right? If I look in a fixed column at a fixed point in time, bring that back up. If I look at a fixed point in time at a fixed column, you see that the density is the same. All I'm changing is how that density is built up by individual deterministic or stochastic trajectories. When I change the definition of the interpolant, I change the definition of the intermediate density. Okay? So what this says is something very different from how people view score-based diffusion, which is that the path in the space of measures is completely decoupled from how you sample that path. Right? You don't have to think about a forward noising process and a reverse kind of generation process. You think about forming a connection between the two densities, and then you ask how you want to sample it. And you're free to sample it with whatever level of noise that you want, whatever is useful for your application. Okay? Everything that I've done so far has been analytical. So all of these densities are the same, right? And from that perspective, maybe you would think you should just use an ODE because it's actually easier to integrate an ODE. But in fact, key insight that has sort of gone overlooked in the generative modeling literature is that when you have approximate models, which is always going to happen when you learn with a neural network for some finite amount of time over some finite amount of data, then the resulting approximate models are all different. As you change the diffusion coefficient, the model is different. And in fact, how these errors propagate through these different models changes. So you can ask if you can optimize over the diffusion coefficient to maximize the quality of your samples. And it turns out that one can characterize the quality of samples in a very similar way to how we formulated that time-dependent Fokker-Planck algorithm from earlier. Okay, so let rho hat tx be the marginal density of my model given by some SDE, where I have some approximate drift b hat, which is some neural network that I learned, and some approximate score s hat, which is, say, also some neural network that I learned. Okay, and here I'm just taking epsilon to be a fixed scalar, but it can be time-dependent, it can be state-dependent. All these things go through. It just makes the notation a little bit more heady. Then one can show the following bound on the KL divergence from the target to the model. Okay, this is a very strong guarantee. It's kind of a likelihood bound. It's sort of celebrated in machine learning theory a lot of the time. The bound is as follows, the sum of two terms. The first is the error in the drift, the L2 error in the drift. And the second is the L2 error in the score. And they're respectively weighted by epsilon and 1 over epsilon. Okay, if you think about these terms here, in fact, they are precisely what we minimize when we learn an interpolant up to a constant. So in fact, what this says is that when you learn an interpolant and you sample with an SDE, you actually maximize the likelihood of your model. Okay, so these results first appear in my paper with Michael Albergo and Eric van den Eenden. I just want to comment that there's a similar result that was shown by Yang Song in this 2021 NeurIPS paper in the context of score-based diffusion. And there it's been kind of a celebrated result and has been the basis of many theoretical papers that perform a discrete time analysis of score-based diffusion, like this paper by Sitan Chen that I'm citing on the right here. And people in the literature seem to think that this kind of guarantee is actually unique to the score-based diffusion process. What I'm showing you is that it actually has nothing to do with score-based diffusion. It's a very fundamental property of stochastic differential equations and Fokker-Planck equations. And in fact, you can derive it directly from a PDE argument. You don't need to know anything about the score-based diffusion process. Okay. Now, we can compare this to the state of sampling with an ODE. So what I'm showing you on the bottom here is going to be a similar kind of guarantee. What I want to consider now is the case where my model is generated from some underlying approximate probability flow equation. So let's let rho hat t be the push forward under some approximate flow map x hat t of some initial condition, rho 0, where my approximate probability flow equation is just given by some learned neural network of the drift B. Well, then one can actually prove an equality for the KL divergence. In fact, this equality was the basis of the time-dependent Fokker-Planck algorithm that I introduced a few slides ago, which is that the KL divergence from the model, from the target to the model, is the expectation of the error in the drift dotted into this error between scores. But again, there's a very subtle aspect of this relation, which is that this is grad log rho hat. It is not S hat. So it is not the score model that I learned. It's not a neural network. It's the score of my approximate distribution. And in general, I have no control over this thing. I really don't know what this score is, and I have no way to enforce that it's actually equal to the score of my target. And so I have no guarantee on the KL. Okay, so what this suggests is that SDEs have stronger theoretical guarantees than ODEs. Of course, the proof is in the pudding, so we need to actually test this. So we ran some experiments on 128-dimensional Gaussian mixtures. What I'm plotting here on the x-axis is epsilon, a fixed noise scale. What I'm plotting on the y-axis is precisely that KL divergence that I was bounding in the previous theorem. Okay, there's 4 curves here. I don't want to dwell too much on the details of the 4 curves. They're basically 4 choices you can make of what you learn in the actual learning algorithm. But what I want to point out is that each of these curves is kind of U-shaped, much like the epsilon 1 over epsilon trade-off we saw in the previous theoretical guarantee. And then every curve has a minimum at a non-zero value of epsilon. Okay, so this is consistent with the theory that SDEs have better theoretical guarantees than ODEs. Now, this is kind of a synthetic example. It's 128-dimensional Gaussian mixtures. It's high-dimensional, but they're Gaussian mixtures. One can also try to test this in kind of real data sets, like image generation data sets. So I'm showing you a result from a recent paper with an amazing undergraduate at NYU, Willis Ma, and also Seining Zia, who's a professor at NYU CDS, and then again, Michael Albergo and Eric van den Eenden. So what I'm showing here is a plot on the y-axis of the FID score, which is a quantitative metric of the quality of generated images that people care a lot about in the image generation literature. On the x-axis, I'm showing the number of function evaluations. This is like the number of discretization points in my ODE or my SDE. And then I'm showing you 4 curves. The green curve is an ODE, and the other 3 curves are SDEs with different choices for time-dependent diffusion tensors. Okay. What we see is that for a low number of function evaluations, the ODE does better. I should say that lower FID is better. You want this number to be lower. So for a small number of function evaluations, ODEs perform better. This is just because it's easier to integrate an ODE than it is to integrate an SDE. But if you have a big enough computational budget and you can have a fine-grained discretization of your sampler, then we actually find that all 3 of the SDEs we tested ultimately perform better than the ODE. Okay, and this is actually a performance gap that people really care about in practice in computer vision. So what are the key takeaways here? Well, defining the path is completely decoupled from how the path is sampled. I'm free to sample it either deterministically with an ODE or with an SDE with an arbitrary level of noise. And in fact, I can tune that level of the noise after the fact without learning again. I'm just free to choose that diffusion tensor. The sampling procedure can be chosen to maximize sample quality after the fact by kind of optimizing over this diffusion tensor. And there's sort of a trade-off between sample quality, which appears to be generated by SDEs. They appear to generate better quality samples, and speed, generated by ODEs because it's easier to integrate ODEs. So if you have a restricted computational budget, it might be better to use an ODE, but if you have big computers because you're working with NVIDIA or something like that, you might get better results if you sample with an SDE. Okay, I just want to wrap up with two kind of fun experiments that highlight the flexibility of stochastic interpolants. So one of these is image inpainting. This is an experiment really led by Mark Goldstein, who's an amazing PhD student at NYU. Okay, so in image inpainting, I'm given a masked image, like I'm showing you on the left here. And what I would like to do is fill in these masks in a manner that's consistent with the rest of the image. Okay, so it's an inverse problem. It's quite difficult. In the context of score-based diffusion, because my base density has to be a Gaussian, I need to start from pure noise. So I can always condition on the part of the image that I know, but I have to fill in the pixels even if I know the answer to them. For stochastic interpolants, because my base distribution is arbitrary, I can choose the base distribution to be the distribution over masked images, and I can form a coupling between that distribution and the target in such a way that a masked image is always paired with the ground truth during training. What this means is that the ground truth velocity field will be 0 in the pixels that are known analytically, and I can always freeze those pixels and just focus on filling in the mask, which is a much easier sampling problem. Okay, so what I'm showing you here are some results from this on this picture of this dog. Okay, what we get is a kind of a remarkably accurate picture of a dog that seems very, very consistent with the ground truth. The one difference is, in fact, that the dog's eye is closed. But if you actually look at the input to the model, you realize that both of the dog's eyes were masked in the input. So the neural network doesn't know whether or not the dog's eye should be open or closed. And in fact, it closes the eye, which is completely consistent with the information that has been given. Okay, so this is a qualitative result. There were quantitative results in the literature for a related problem known as image super resolution. So in image super resolution, I'm given a coarse grained image, and what I would like to do is map it to a kind of high resolution version of that same image. So again, kind of a difficult image, a difficult inverse problem. And yet again, in the context of score-based diffusion, I somehow need to start from pure Gaussian noise, and I can condition on the low resolution image, but I'm kind of throwing all that information away, except for the conditioning information. In the context of stochastic interpolants, I can start my sampler from the coarse grain image and just focus on filling in the high resolution details. So again, it's a much easier sampling problem because I can tailor the base to the target. Okay, so what I'm showing you in this table is a collection of quantitative results for this problem. Again, this FID score, which is kind of the standard quantitative metric where lower is better. And what we found is that we actually obtained state-of-the-art results using our method, and we did so using significantly less compute. In fact, this I2SB paper with this FID score of 2.7 was published by NVIDIA. So they have sort of unlimited compute in comparison to us at NYU, and yet we were still able to do a very good job in comparison to previous results. Okay, so that's all I wanted to say. Just wanted to wrap up there, showing kind of the trade-offs between high-dimensional scientific computing for Fokker-Planck equations and generative modeling with Fokker-Planck equations. Thanks for the invite, and I'm open to any questions.
Thank you so much, Nicholas. That was a really nice talk. Do you have any questions from the audience?
Yes. Hello, this is Chen from Brown University. May I ask a few questions?
Hey, yeah, absolutely.
Yeah. Hello. So in your page 7 and 21, you've mentioned there are transport
Turn on your video,
maps.
Jan, turn on your video so people, Nicholas
yeah.
can see.
1 second. It's a little bit.
Okay, you're good. You're good.
Okay, yeah. So yeah, in your page 7 and 21, you mentioned the transport maps 2 times.
Yeah.
Well, you kind of transport one of their distribution to the other distribution. And I'm quite interested, is this somehow related to the optimal transport questions? Is this kind of transport optimal in some sense, or you do not care about it if it is optimal in any way?
Yeah, so great question. Let me just clarify. You said page 21. Is this the slide that you were
Yes,
thinking about?
exactly. Yeah, I see different ways of doing the transportations. I don't know if any of them is the optimal, or you do not need to do the optimal transporting in this sense.
Yeah. So in fact, if you look at this objective function for the velocity b here, so if instead of taking a linear interpolant, like I wrote down earlier, maybe actually let me go back a few slides here. Instead of taking this linear combination here, if you parameterize the interpolant in a nonlinear fashion, say using a neural network that has the right boundary conditions, IT of x0 and x1, and then when you learn b here, you minimize over your neural network model for b, and you maximize over the model for I, you recover optimal transport. So you get optimal transport if you solve a more difficult min-max problem.
I see, yeah.
In the context of generative modeling, it's actually not clear that we want to solve that min-max problem, right? Because while optimal transport has straight lines, which means that you can sample very easily, for example, the resulting velocity field can be very nasty and might be really hard to learn. So there's kind of this trade-off between you want the velocity field to be easy to sample, but you also want it to be easy to learn. And we find, in fact, that using kind of like very simple choices for the interpolant often work best in practice. So this is, in some sense, very suboptimal transport, but it works very well for the purpose of generative modeling.
Okay, I see. And for your page 11, you've done the batches over the particles. May I assume that this is kind of, you have proved this is an unbiased estimator?
In what sense? I mean, it's an exact relation for the loss, right? So it is an unbiased estimator. I mean, if you want to know whether or not, say, an expectation over the particles is an expectation over the data, that I believe is an open question. It should be true in the thermodynamic limit, but we did not prove that. No.
I see. Okay, thanks. Yeah. So in the next page, you've also mentioned that you are using the score function to do this like the, yeah, exactly here. So you've used the score function instead of the local gradients. Is this a good way to kind of avoid computing a local gradient because it's very expensive in the ping loss?
I'm not sure I understood the question. Could you repeat
sorry,
it?
yeah. So in this case, you've mentioned that this is a ping loss here. So number dots v rho as you expand this. So I see there is a gradient for log rho here. If you directly put the gradient for log rho, it might be quite expensive. So is this why you replace the log rho, gradient log rho with the score function?
Yes, yeah, totally. I mean, so there's several reasons, right? One is that it's more expensive. Another is that when you have this extra gradient, you're kind of killing some of the signal during the optimization because the more gradients you take, the more localized your activation functions become.
Yes.
Maybe this is something that you guys have fixed with these like adaptive activation functions, but we didn't use those. So yeah, we wanted to avoid a gradient. In the context of score-based diffusion, it's kind of well known that they get better results if they parameterize the score directly rather than parameterize log rho and take a gradient. So we just followed those practices. Another issue is that if you parameterize log rho, it's permutation invariant. If you parameterize grad log rho, it's permutation equivariant. So transformers, I think, are very natural for permutation equivariance. Permutation invariance is actually harder. There's something called a transformer. I tried it and it didn't work as well.
Okay, I see.
Yeah, there's like kind of several nested issues here.
Yeah, so I remember that in some sort of, if you fix the query sequence, if you permute the key and the values, it could be invariant, but that will kind of alter your structure quite nasty, I guess.
Yeah,
okay, thanks.
Exactly.
Yeah, one last technical questions. In your next page, you mentioned that you kind of putting each particle as a token for your transformer model. So may I ask how long the sequence could be, or should I say how many particles you can handle at in the same batch?
Yeah, so I mean, we have results here for 32,000 particles, right? Like precisely with this architecture. But the key is that we parameterize the score at the particle level, and we assume by spatial locality that the score for a given particle only depends on a local neighborhood, right? So that's really key for using this transformer architecture because of the quadratic complexity with the number of tokens.
Yes, so I guess you can kind of, in this case, you just train the transformer model with a relatively small n, and in the inference stage, you just expand the length, so you can do compute more and more particles at the same time.
So in a sense, yes, but at the same time, maybe not quite what you're suggesting, because I think you need enough particles that something interesting is happening. Like if you trained with only 64 particles, I don't think it's going to really reflect the underlying dynamics, and it probably won't generalize to such higher dimensional systems. Although I haven't tried, so it's worth trying.
Okay, yeah.
We train on 4096, which is still too much for a transformer, at least with our resources. I mean, OpenAI can probably do it, but I can't. But I use 64 neighbors in my ansatz, right? So then there's only 65 tokens counting the current particle, and that I can handle, and it works well. And we tried more and we tried less, and we found that 64 was kind of a sweet spot. We have no proof, but we just laid it over this choice.
Yeah, so for the 64 neighborhoods, are you trying to kind of enforcing the 64 neighbors by positional encoding, or somehow the transformer learned it by itself?
Not quite either. So I mean, I define a transformer architecture that takes in a fixed number of tokens, and then when I'm computing the score for a given particle, I compute, say, the 64 nearest neighbors, and I pass those as tokens. So there's no positional encoding. Positional encoding would integrate the equivariance that I need. And I also don't learn the number of neighbors. In fact, if you know how to do that, that would be interesting, but I'm not aware of a transformer architecture that can like adaptively learn the number of tokens.
Okay, I see. Thank you very much.
Yep.
Great. Do we have any other question?
Maybe Zheng Yuan, who stay up, he's from Singapore, he stay up to, what is it now, 3 o'clock in the morning.
Wow. Thank you.
Maybe he has a question to ask. Zheng Yuan, you're still awake? Yeah. Okay.
So actually, before this talk, I watched your colleague Michael's talk on YouTube, and I already know your work called SIT, stochastic interpolant transformer. You work with other collaborators. So, well, if you want to sample by your stochastic interpolant, you still need to solve SDE or ODE, right?
That's
like
right.
discretization.
Yeah.
Also on 0 to 1. So actually, there's something called consistency model. So they are kind of another kind of diffusion model that can infer or generate images by only one step. So I'm thinking about if we consider consistency models which do not require any step, can your stochastic influence still be faster than these kind of consistency models? By the same author, Yang.
So we have many results on interpolants, right? And I've kind of focused on this Fokker-Planck angle because I've worked a lot on the Fokker-Planck equation. But there's a whole thread on interpolants about relations to existing generative models in the literature. In fact, we have this big paper on arXiv, stochastic interpolants, a unifying perspective. It's the one with Michael and Eric, where we kind of highlight connections to many existing models. One such important connection is that in fact, score-based diffusion is a specific choice of alpha, beta, and gamma here. So this is a strict generalization of score-based diffusion. And it's a strict generalization that lets you compress things to finite time if you want, but you could do it on infinite time like score-based diffusion. And so in that sense, everything that has been done in the context of consistency models can also be done here. Actually, what a consistency model does, kind of at a high level, is it learns in ODE, right? Like it learns like this probability flow equation on the left here. And then it says, well, if I actually knew the flow map of this equation, I would just use x1 of x, and then I would just have a one-step sample. So it takes a learned ODE, and then it kind of distills it by learning the flow map for that ODE. They also have ways to kind of train the flow map directly, but morally, this is what they do. And we can do the same thing, right? You can always kind of distill this probability flow equation into the flow map and then sample very quickly.
Okay, I see. So actually for so in this figure, actually something related to optimal transport. So there's actually another kind of generated model considering optimal transport called Schrödinger bridge. So their formulation seems to be very similar because they consider finite time and also transporting, interpolating one distribution to another. And these two distributions are not restricted as diffusion models. They require one to be Gaussian. So I'm not sure the connection and difference between the stochastic interpolants and Schrödinger bridge. And I noticed that in one of the papers by a group in Oxford, they claimed because they may call your model like flow-based generated model or score-based. So they claim that Schrödinger bridge can generalize these two kinds, I mean, flow-based and score-based. So I'm not sure what's your opinion on their paper and their, so on the Schrödinger bridge.
Yeah, so I mean, there's many perspectives on all these kinds of models, and many people are doing a lot of work on them, and kind of different people have different ways to view what's going on here. So again, I would say that you can get a Schrödinger bridge out of these kinds of models. One way to think about Schrödinger bridge is that it's kind of like a regularized optimal transport in a sense, where you kind of are trying to minimize the kinetic energy of the transport subject to a Fokker-Planck equation, right? So in fact, earlier there was a question about if these models are related to optimal transport, and I said if you parameterize the interpolant and maximize over the interpolant, then you recover optimal transport. In fact, if you do the same thing while incorporating this term gamma that I have here, then you recover Schrödinger bridge. So there's a way to get Schrödinger bridge out of this formulation by solving a min-max problem. But again, I think at least to Michael, Eric, Mark, and I, kind of the Courant community working on this, it's not totally clear to us why one wants the Schrödinger bridge in the context of generative modeling. like Schrodinger posed this problem kind of from a physics perspective about trying to find the most likely connection between two particles. It makes a lot of sense in that context. Here, Schrodinger bridge kind of has a notion of optimality that it's not totally clear is actually relevant for generating, say, images in practice. So we can recover the Schrodinger bridge, but we often choose not to when we try to train a generative model. Yeah, I'll also just say that there's also been a lot of interest kind of sort of parallel to Schrodinger bridge in the context of Falmer processes. And we're writing another paper now on the relation between stochastic interpolants and Falmer processes, which will come up very soon. So Falmer is like a Schrodinger bridge between a point mass and the target. And we can also do this kind of thing.
So basically, as you mentioned, there's actually not a clear relationship between the paths, So maybe some people resort to optimal transport paths, but actually the benefit isn't clear. So I think you are actually manipulating the paths between the two distributions, right? So I'm not sure if different paths can lead to a difference, because as you're showing in your theory, what you are minimizing is the KL divergence between your model and your model distribution and the target distribution, but the path is actually agnostic. So I'm not sure if the path can make a difference if you choose different gamma t.
There's a very important distinction here, right? So the one-time marginals are the same in the sense that the path in the space of measures is the same, but the paths of the individual samples are very different, right? You can see that from this picture here. So if you look, say, in the first column where gamma is 0, and then as you go down in the rows, and I'm changing the diffusion coefficient epsilon, the paths are completely different. And this does have practical ramifications, right? Like it's a lot easier to integrate the paths for epsilon equals 0 than it is for epsilon equals 5, for example. So there are trade-offs both in terms of sample quality and in terms of computational expense when you train the paths. But it's important to keep in mind that there's two paths at play, right? There's the path in the space of measures, and that matters a lot. And that's sort of what we think about when we talk about optimal transport, for example. Then there's also the paths that are kind of used to realize that path in the space of measures, the level of the individual samples. Both of these paths have practical ramifications.
I see. Yes, thanks for your answer. So actually, no more question, but I just want to mention that actually we have another paper, our paper on score-based physics in neural networks. So I think we consider maybe corresponds to the first part of your presentation. So actually, we use score function from a very similar perspective. We want to solve for the probability density function, but as you know, it is decaying exponentially if we consider Gaussian. So our motivation is that the score function is very numerically stable, because the score function of a Gaussian is just a linear function. It is not decaying or increasing, so it's numerically stable to model in very high dimension. So previous approaches in PIN literature to solve Fokker-Planck equation it directly solve the PDF density, probability density. So they will incur some numerical issue in very high dimension. So that's our initial motivation of using the score function, and we solve for density instead of the entropy you are looking for. So I think that's one interesting thing. We resort to the same score function for something, some different motivations. Yeah, so I just clarify a bit. Yeah, so that's all for my question.
And
Yeah,
Nicholas,
thanks.
on that, in 130,000 dimensions, how do you compute? You cannot use Monte Carlo to compute the. So how do you get the ground truth raw?
Yeah, so this is a great question. So we don't have the ground truth raw, right? We don't know the accuracy of the solution. We can verify invariance. For example, because the system is at stationarity, you know that the entropy should be conserved over time, and you can check things like that. And we can get, say, a few digits of relative accuracy, like 2 or 3 digits of relative accuracy for high dimensional systems. But yeah, I mean, actually checking numerical precision against the ground truth, the problem is interesting because no one knows the ground truth, so it's tough to say. Yeah.
Well, you can fabricate solutions, but I mean, in general, we have this problem. That's why I'm asking you.
Yeah.
Monte Carlo breaks down around 30 to 40. I think we have an example of 50 dimensions, I think, where they cannot get the raw right.
Especially when dealing with some long tail distribution, if we consider convolution between two Gaussians, then that's okay if we sample a lot of points and get an accurate result. But this accuracy actually decays with respect to dimensionality. So Monte Carlo also suffer from the curse of dimensionality.
Yeah.
So to test our model, we have to resort to some analytically solvable problems like OU process you mentioned, also geometric Brownian motions, and
Yeah.
consider some complex initial conditions, initial distributions like other Laplacian or Cauchy distributions to test the model because they are solvable. If we consider general drift or diffusion coefficients, then it is not analytically solvable. Then there's no test, there's no labels in high dimensions. So that's very hard to benchmark the accuracy of the model. As you mentioned, maybe one method is to test the moments because as you mentioned, you test variance. So it can be regarded as second moments, so we can test third moments, fourth moments, but that may not be comprehensive in high dimensions. So that's what we thought about during the experimental design.
But anyway, Nicholas, the omission of your paper was not intentional at all. Thank you for bringing this to our attention, and thank you very much for giving this two excellent talks, actually. But it was a unifying theme, so that's this is great. So I will let Juan close the session. We are already past, but it was a great discussion.
Great.
Yeah, thank you very much. Thanks for hosting me. I really appreciate it.
Thank you so much, Nicholas, for your time, and thank you, everyone. That this will be the end of today's seminar. See you next week, and enjoy the rest of your weekend. Bye.
Thanks.